The Earth was formed precisely 4.57 billion years ago. Its formation occurred more than 9 billion years after the birth of the universe. We cannot succeed in understanding the place of the Earth if we do not put it in the context of the universe and its history. Let's go back briefly to where it all began. 13.8 billion years ago, all the matter of the universe was born. A primordial atom, dimensionless and infinitely small, which contains all the energy of the universe. This precise moment is called the Big Bang. The matter and energy of the universe, as well as the dimensions of space and time, are compressed in a state of extreme density. The temperature is high, and it is in this burning environment that all matter is organized. "30 minutes after the Big Bang, the universe reaches a temperature of 300 million degrees and a density of almost zero. Nothing happens for a few 100,000 years. The universe continues its expansion. Its radiation prevents the heaviest elements from forming because they remain unstable. The hydrogen and helium nuclei are bathed in a sea of photons. More than 300,000 years later, the temperature reaches 3,000 degrees Celsius, or 5,432 degrees Fahrenheit. New bonds take place. It is the recombination, and the universe becomes transparent. A first sudden emission of light arises, called the cosmic microwave background. It is a great step in the history of the universe, which is suddenly illuminated. The glow of this cosmological background is propagated to us since that time. One million years after the Big Bang, the universe is homogeneous. Its temperature reaches minus 173 degrees Celsius, or minus 279 degrees Fahrenheit. It contains no stars. The only light is that of the fossil radiation. It continues its expansion. Gigantic masses of matter are moving away from each other, and clouds of hydrogen and atoms are gathering under the effect of gravity. Denser and denser clouds are formed. These are the protogalaxies. These present inhomogeneities, resulting in areas where the matter will strongly condense until the birth of stars. The first galaxies take shape 12 billion years ago as islands of matter bathing in the intergalactic void. Stars are born everywhere. Then, a few billion years later, the first clusters of galaxies take shape. Some of the newly formed galaxies group together in a cloud, which is called a cluster. The future Milky Way is in its embryonic stage. It has its origin in the meeting of protogalaxies. The local supercluster, Ediacaran, the basin of gravitational attraction towards which the galaxies and clusters of galaxies are moving, was formed 6.8 billion years ago. It is similar to a gigantic cosmic continent consisting of 100,000 large galaxies, including the Milky Way, each containing about 100 billion stars and 1 million dwarf galaxies. The local group is the aggregate of galaxies in which the Milky Way is located. $4.6 billion years ago, the solar system begins its formation. Everything begins with the birth of the star of our solar system, the Sun. Dark energy is the main constituent of the universe. The local supercluster counts more than 10,000 celestial objects. At its periphery is the local group, consisting of about 30 galaxies, of which the Milky Way is the most prominent. Its dark matter halo has given it a thin disk formed of stars and gas, generally very cold and quite diluted, since it contains only a few tens of billions of atoms per cubic centimeter. One of these interstellar clouds floats 27,000 light-years from the center of the Milky Way. It is composed mainly of hydrogen, with a few hints of helium, and other heavy elements from a supernova. A fragment of this nebula suddenly collapses on itself under the effect of gravitational attraction. The atoms accelerate and migrate towards the center, which becomes hotter and denser. The cloud adopts a spherical shape, and the gas heats up to radiate energy. The sun in the making is for the moment in the form of a protostar. In order to shine like a star in this excessively cold environment, reaching a temperature below 270 degrees Celsius or 518 degrees Fahrenheit, it must produce enough energy. The gas cloud contracts until it reaches a temperature of 10 million degrees Celsius, or more than 18 million degrees Fahrenheit, at its center. The fusion of hydrogen nuclei starts. The strong interaction dominates over the electric repulsion. The two hydrogen atoms combine to give an atom of helium and thus release energy. Up to 4 million tons of hydrogen burn by fusion every second, and the energy produced in this furnace at 15 million degrees Celsius or 27 million degrees Fahrenheit must be released. Photons produced in the center of the sun take on this task and will take 500,000 years to reach the surface. From the burning core, they cross a colder, radiative zone at 2 million degrees Celsius or 3.6 million degrees Fahrenheit, and denser than a convective zone where the hot matter dissipates towards the colder outside. At the end of this journey, the matter cools down and goes back down to the bottom. Before its final contraction, the future sun is surrounded by a disk of gas and dust, which fragments into small bodies. Among these, some agglomerate into larger structures and form the planets. The disk of gas thins outward due to the decreasing gravity and is constantly fed by the dust that swirls around the young sun. The movements of the particles generate heat that dissipates in the infrared radiation range. The solar wind drives the gas and volatile compounds towards the external zones, which are colder. The frost line is formed as a boundary between the internal world, in which the ice is not stable, and the external world, in which the ice survives. Outside this line, the embryos are rather massive and manage to attract gas and coat themselves with hydrogen and helium. They continue to grow, and when the mass of this envelope reaches 100 times the mass of the Earth, it collapses on itself and gives birth to gas giant planets. This is how Jupiter and Saturn appeared. The second possible scenario is that the planetary envelope disperses, leaving behind a large core of rocks and ice, like Uranus and Neptune. On the other side of the ice line, the environment is gradually depleted of its gas. The planetary embryos evolve and are sometimes brought to cross each other, which generates violent collisions between these embryos of several hundred kilometers in diameter, whose orbits are close. These shocks release a disproportionate energy. Only 4 objects will survive and will be qualified as telluric planets. Among them, the Earth. The telluric planets are formed later and more slowly than the gas giants, which seems paradoxical since they are smaller. The telluric planets all have a mantle and a core, but each has its own particularities. The closest to the Sun is Mercury, then come Venus, Earth, and Mars. Here we come to the moment that interests us, the birth of our planet Earth. The history of the Earth begins here, 4.57 billion years ago. The young Sun in formation is surrounded by grains of dust that revolve around it. These materials are much too fast and do not manage to reach it. They spread out in the form of a disk, thinner in its center, made up mainly of hydrogen and helium, and strewn with tiny aggregates of substances in the solid state. Like the dust that gathers in sheep behind the furniture, the grains of substances gather and agglomerate with each other. When they reach a diameter at least equivalent to 800 meters or 2,600 feet, gravity comes into play. They suck up the surrounding dust and take the form of objects of several kilometers. These young and huge planetesimals absorb all the substances that are in their area of influence, and this is how planetary embryos are formed. They then collide with each other and merge until they give birth to some planets, including the Earth. The accretion mechanism of the Earth is controlled by a gravitational rush of larger and larger bodies from a dust disk. This scenario is declined in 3 steps. In a first step, the dust grains are close to the symmetry plane of the nebula. They agglomerate by collision at low speed. Bodies of 10 kilometers or 6 miles in diameter are gradually formed. In the second time, the attraction of the matter towards the largest bodies is much more important than towards the smallest. Their mass increases exponentially. It is the gravitational runaway. Objects of several tens of kilometers, or half of diameter, evolve until they reach gigantic sizes of planetesimals of several hundreds of kilometers, or half of diameter. These first 2 stages last less than 3 million years. In the third and last stage, the growth stops when the mass of matter in the feeding zone is accreted. Only bodies of the size of small planets with eccentric orbits remain. This last stage is longer than the first 2. Several tens of planetesimals of the size of Mars form at this time in the inner disk. They eventually collide with each other until they gradually build a planet. How do accretion bodies of a few tens of kilometers, or half of diameter, form planetesimals? The separation of the silicate mantle and the metallic core takes place before the accretion of the bodies. The bodies have upstream accumulate enough heat to trigger this fusion. This is possible for relatively small masses because of the energy released by the decay of radioactive elements at short period. The dust is the element which constitutes the colossal mass of an interstellar cloud. It is from it that planets take shape. Let's take a closer look at cosmic materials to determine the nature of the initial stock of chemical elements that were used to make the Earth. Interstellar dust clouds are obstacles to the transmission of light. They weaken the light intensity and modify the light spectrum. This proves proves that they contain a wide variety of compounds, mostly silicates, carbonaceous molecules, and pieces of carbonaceous material. But these dust grains hide an even greater diversity, because each porous agglomerate contains elements which themselves contain subgrains of submicrometric or even nanometric size. Some of them are of pre-solar origin, such as nanodiamonds, silicon carbide, or corundum. The rest of the components of cosmic dust come from chemical reactions specific to the interstellar cloud or triggered by reactions between the protosun and its internal disk. Chondritic meteorites, which have chondrules, are the most abundant and primitive material of the solar nebula. Chondrites contain the original elements from which the Earth and other terrestrial planets were formed. Their composite material is formed of particles of a few microns containing microscopic minerals and carbonaceous molecules. This binder holds together the mineral inclusions rich in calcium and aluminum, and the chondrules. It can only be formed during the travel of the objects in the zones of the disk far from the Sun, because the temperatures are sufficiently low not to alter the most fragile compounds. Propelled by the solar wind, the chondrules are covered during their journey by a thin film of clay particles in the form of a crown. The mineral fraction of the material contains, in addition to olivine and pyroxene, hydrated species. These clays are essentially magnesian or ferrous and contain very little aluminum. Apart from clays, carbonation chondrites contain very complex organic molecules like amino acids or sugars. But then, what was our terrestrial planet made of 4.57 billion years ago? Carbonaceous chondrites are the most primitive elements that were formed in the solar nebula. It is from these initial atomic proportions that the planetesimals and then the planets were formed. The correspondence of the composition of the external corona of the Sun and that of the chondrites is quasi-perfect. The processes of transformation of the Earth since its formation only reshuffle the stock by moving some elements from a reservoir to another. The Earth was formed in a dry part of the solar system. The ice limit, beyond which the solar system contains icy bodies, or mineralogically constituted of water, is located much further than the orbit of Mars. The presence of water is therefore surprising, especially since the Earth will be the only planet to have it. Although part of the water is brought by meteorite collisions, it turns out that the other part comes from the famous chondrites that made up the Earth, since they can be rich in water, up to 20% of their mass. The water on Earth results from a mixture between two different sources, carbonaceous chondrites and comets. The first 100 million years after the birth of the solar system are decisive in the formation of the internal structure of the telluric planets. It is during the existence of the generalized magmatic ocean that the gravitational migration of elements towards the center of the planet Earth, but also of the Moon, occurs. Their accumulation builds little by little the core. This differentiation occurs in barely 30 million years, a very short time that implies an efficient mechanism. What really happened? It all starts with a thermodynamic equilibrium that splits the metal in the silicate liquid, whose densities are different. The denser phase, perpetually subjected to an agitation effect, ends up agglomerating into fine droplets of about 1 centimeter in diameter, that scatter in the magma. They are then driven by their weight towards the center of the planet and stop at first at the transition with the solid mantle. Here they will undergo new modifications in their composition. They integrate some elements lighter than iron, like sulfur, silicon, or oxygen. But at a depth of 1,500 kilometers, or 930 miles, the pressure is immense, more than 45 gigapascal, and especially too important for the temperature of 3,500 degrees Celsius, or 6,300 degrees Fahrenheit, to maintain the silicates in the molten state. The depth of this transition is determined by the intersection between the beginning melting curve and the geothermal gradient. The iron accumulates by forming pools of varying size. As soon as their mass exceeds a certain value, the density contrast is sufficient for them to pass through the solid matter in the form of gigantic drops, called diapirs. Their coalescence gradually forms the core of the planet. It is completely melted at the beginning of the history of the Earth. With time and cooling, a solid seed is formed, where the pressure is more important, that is to say, in the center. Its rotation in the metallic liquid generates a magnetic field by dynamo effect. However, not all the siderophilic elements are found in the core. The partition coefficient between the two parts varies according to the pressure, the temperature, and the oxygen content. The fineness of the chemical equilibrium that comes into play between metal and silicate leads to deviations. Only 1/3 of the iron is integrated in the core. A large amount persists in the mantle, along with other siderophile elements. The core of the Earth takes nearly 30 million years to form. In terms of geological time, this is a very short time. Its completion corresponds to the giant impact it underwent at the origin of the Moon. The core, at its completion, is a reservoir of liquid iron, but has no solid seed. Its shape is not a perfect sphere, and its center and that of the planet may not coincide. The iron and nickel are accompanied by other elements in their migration towards the center, mostly light elements like oxygen and silicon, representing about 10% of the total mass of the core. The formation of a solid seed is impossible because of the extremely high temperature. This has a significant consequence on the emergence of life, because in the absence of internal dynamo, the Earth is deprived of magnetic field. The Earth in its primitive form is a ball of molten lava. It is continuously hit by bodies and meteorites, making the rocks enter in fusion at each place of impact. These are innumerable, and the planet reaches up to 4,700 degrees Celsius, or 8,500 degrees Fahrenheit, at its surface. After 100 million years, the surface of the planet is covered with a crust of frozen rocks of basalts and comatites, which cracks and drifts with the effervescence of the depths. The mantle of the Earth is solid, and is made of a part in olivine and another in perovskite. The still relatively high temperature stimulates the convection cells that continue to stir these materials. Their viscosity does not yet make them a completely solid structure, and they are continuously deformed. After 160 million years, the generalized magmatic ocean is completely crystallized. After the exponential growth of its mass, the young Earth goes through a period of calm, during which the meteoric impacts decrease considerably. Once 90% of its mass has been accreted, a major event occurs, thanks to which the Earth will reach its current size. A last giant impact with the planet Theia. The young Earth continues its evolution. Its accretion is almost finished. Following the period of gravitational runaway, it has reached 90% of its current mass. It has cooled down and reached a temperature of 1100 degrees Celsius, or 2012 degrees Fahrenheit at its surface. The solar system continues to be violently bombarded by asteroids. Although its accretion zone is cleansed, the Earth will then undergo an important collision with another protoplanet of the size of the planet Mars, a celestial companion transiting on a neighboring orbit, which answers to the name of Theia. Theia violently impacts the planet. A significant amount of material is ejected far from the Earth. Theia is completely dislocated, as well as the external layer and part of the mantle. A large part of the iron of its core is transferred to the Earth. A ring of debris is formed around the Earth, and then accrete in a very short time, about 100 years, and form a satellite, the Moon. The energy involved in the impact is considerable. Billions of tons of material are melted and vaporized. In some parts of the Earth, temperatures of up to 10,000 degrees Celsius, or more than 18,000 degrees Fahrenheit, were recorded. The outer layer of the Earth melts into an ocean of magma over 1,000 kilometers, or 620 miles deep. The melting of the silicates generates a silicon-poor magma. The original silicate solids that are denser make up the lower mantle. The alloy of iron and nickel, which is even denser, migrates towards the center and carries with it elements with a strong affinity for iron, such as platinum, gold, iridium, or tungsten. The Earth is similar to a lava empire. It is now made up of a liquid core of about 3,400 kilometers, or 2,100 miles in diameter, a lower mantle, 1,900 kilometers, or 1,200 miles thick, and an upper mantle, the magma ocean, 1,000 kilometers, or 620 miles thick. The fusion of the upper mantle let escape almost all the gases. An atmosphere begins to form. The Earth has neither water nor crust. The solar system is then much too hot to allow water to exist in liquid form. It does not contain enough hydrogen for its oxygen to form water. The energy required to agglomerate the material in orbit around the Earth is sufficiently large to also melt part of the Moon and create a lunar magma ocean of several hundred kilometers, or half a mile in depth, composed of molten silicates. Due to its relatively small size and lack of radioactive elements, this magma is not kept in a liquid state for very long, just long enough for accretion. The newly formed Moon has a relatively small iron core. This is explained by the fact that the core of Theia has mostly merged with that of the Earth. The Moon will keep the scars of this shock. The Earth will be reshaped by volcanic activity and erosion. The collision causes the tilt of the axis of the Earth of 23.5 degrees, which generates the seasons. The Earth's axis is the imaginary line that connects the North Pole to the South Pole. It is around him that the planet makes its rotation. During the collision between Theia and the Earth, this axis of inclination is derived from the ecliptic plane, the plane of the Earth's orbit around the Sun. The axis is always directed in the same direction, but during a part of the year, the northern hemisphere is inclined towards the Sun, Then, during the second part of the year, it is the southern hemisphere. The sun heats more the temperature inclined in its direction when it is summer. It heats less the opposite hemisphere when it is winter. During spring and autumn, the sun provides a similar amount of heat to both hemispheres. The couple, Earth-Moon, of considerable dimensions and being located at relatively close distances, will undergo the effects of the gravitation, what will cause the phenomenon of forces of tides. The Moon will have effects on the parts of the Earth that are closest to it at a given time. The point of the Earth's surface facing it will be more affected by the force of gravity than the point of the surface opposite it at the same time. The Earth is subject to differential forces that will stretch it towards the Moon and compress it towards the poles. The most obvious effect of this influence is on the least rigid part of the Earth, the ocean. Its liquid state reacts easily to the influence of local gravity, which generates the phenomenon of tides. The two bulges of the Earth being symmetrical, a given point will undergo 2 high and 2 low tides per day. The Sun is also involved in the tidal phenomenon. It is located much further from our planet than the Moon, but it participates in the creation of a tidal force equivalent to half that of the Moon. It is the sum of the tidal forces coming from the Moon and the Sun that determines the real amplitude of the tide. The tidal forces will also have an effect on the rigid parts of the Earth. The Earth's crust is thus stretched in the direction of the Moon under its influence. If the Moon and the Earth had identical rotation periods, the bulge would be constantly pointed towards the Moon. However, the rotation of the satellite is much slower than that of our planet. The bulge of the Earth is rigid and driven by the rotation of the planet itself, which makes it gravitate faster than the Moon and point ahead of its movement. The gravitational attraction of the Moon on the bulge will direct it backwards and prevent it from following the movement of the Earth. Over millions and billions of years, this gravitational gain will slow down the rotation of the Earth and will increase the orbital moment of the Moon, which will cause a progressive distance of this one and a decrease of its speed of revolution. The period of rotation of the Earth increasing and that of the Moon decreasing, the two objects will converge towards a situation of synchronous rotation. From this moment, the Moon will always present its same face to our planet. The surface of the Earth is covered by a layer of magma during its first millions of years of existence. The continents are not yet formed. The oceans that form are vaporized from time to time because of the impacts of giant asteroids. The sun shines weakly at this time. The Earth underwent many collisions which caused the release of a gigantic amount of energy and melted some of its matter. The ocean of magma that covers its surface and on 1,000 kilometers or 620 miles deep reaches 2,000 degrees Celsius or 3,600 degrees Fahrenheit and rejects hydrogen, water vapor, carbon dioxide, silicates, nitrogen. The Earth undergoes an enormous degassing. The atmosphere thickens. It becomes stifling and darkens the sky. The pressure is unbearable. The heat that radiates into space has, however, a significant effect. It makes the temperature on the planet fall. The Earth cools down, and under the influence of radioactivity, its core heats up. Convection movements take place. The material that makes up the mantle rises towards the surface at the level of the ridges by a few centimeters per year, then falls back down at the level of the subduction zones. the heat is expelled on the hardened surface in the form of volcanic eruptions. A few fragments of crust appear here and there, like small islands floating on a viscous magma. The volcanoes, in turn, release gases into the atmosphere. The water of the magma dissolves and will decrease the density of the latter to the point that the crust can no longer float. The lavas are at this time composed of comatitic basalts and comatites forming a continuous series between a pole, very rich in magnesium, and poor in calcium and aluminum. Comatites are a kind of petrographic fossils coming from the fusion of the mantle, rocks essentially composed of olivine and pyroxene. No more volcanoes produce them today. Subjected to high temperature, these lavas have a very low viscosity and flow like water. At the interface with the atmosphere, these lavas undergo a thermal shock, which generates the formation of skeletal crystals of olivine, which resemble fish bones and become entangled. The crystallization of the densest minerals occurs at 1,000 kilometers, or 620 miles. The magnesium silicate takes the structure of a perovskite. At the surface, the irregular pack of rocks frozen and fragmented by the turbulence of the magma and by the meteoric impacts that do not cease, begins to flow fragments after fragments. It is therefore the differences in density that will define the structure of the magmatic ocean during its cooling. These differences in density are themselves related to the water content and the difference in pressure depending on the depth. The crustal fragments plunge downward to the magma density transition limit at 250 kilometers or 155 miles. This is also where olivines that float up from the depths accumulate, and where dunites, solid rocks that isolate two compartments of the magma ocean, form. The two spaces shrink as the Earth's heat escapes and the dunite zone expands both upward and downward. Violent turbulences fall on the Earth. The upper part is strongly disturbed, and mobile ice flows of basalt rocks move on the surface. The Moon is located at only 25,000 kilometers from the Earth. That is to say, at only 15,000 miles from the Earth, and triggers gigantic tides. The mass of magma gives off unbearable heat, yet in some places on the surface it is cold. The solar energy is rather weak and is compensated by a powerful greenhouse effect of an atmosphere filled with carbon dioxide, methane, and hydrogen sulfide. It occurs an energy deficit which causes the solidification of the lava. Packs of basalts and comatites, partly serpentinized, float and are displaced on the upper part of the magmatic ocean. A strong thermal gradient is established between the surface and the depths, and numerous very active convection cells are formed. The protocrust that forms above the magma ocean is described as an ice pack whose elements drift, but the composition of the lava at that time and its reaction with water played a big role. The Earth, which is very hot, maintains several convection cells. Their ascending branches emerge at the surface in the manner of volcanic chains comparable to the mid-oceanic ripples that limit the plates and produce a lot of lava. Their gigantic cumulated length allows them to evacuate internal heat. Nevertheless, even if the conditions are extremely difficult, liquid water exists at the interface with the atmosphere, since proto-oceans form and reform even after undergoing impacts that vaporize them. Aqueous alteration reactions cause the formation of magnesian clay at the surface and the transformation of olivines and pyroxenes into serpentine at depth. Recycled in the magmatic ocean, these minerals serve as a carrier to introduce water molecules in what will form the upper mantle. Water is everywhere. It decreases the melting point of silicates and thus allows a melting at a lower temperature. It is a real water cycle that is set up between the rocks and the atmosphere. The more the heat of the Earth is evacuated, the more the rock ice flows are formed. These islands are surrounded by water, the oceans, which begin to become permanent, fed by continuous rainfall. The primitive plates collide. Their fragments fall into the underlying molten material. They mix and give birth to new forms of magma that rise to the surface due to their low density. The volcanoes are fed and reject lava richer in silica. A few kilometers from the interface with the atmosphere, they crystallize and form plutons, massive rocks composed of feldspars, micas, and quartz. The latter constitute a particular family of rocks, whose history is supported by crystals called zircon. This mineral of the Earth's crust is used nowadays for radiometric dating because of its strong resistance to chemical changes. It takes the form of crystals or grains in igneous and metamorphic host rocks. It remains in the future in very low abundance because plate tectonics implies a recycling of materials. When the rock is buried deeply, it becomes heated and can melt or recrystallize. These rocks in formation are the beginning of real continents. Their density is lower than the magma below them, so they float on the surface. Attached to the plutons, they form cratons, the outlines of future continents. The Earth begins to take shape in the structure that is more or less familiar to us. The Earth has cooled down a lot. The temperature of its oceanic crust in the subduction zones is increasing by only 15 to 20 degrees Celsius per kilometer. That is an increase of 68 degrees Fahrenheit per mile. The metamorphic reactions it undergoes produce water continuously due to the destruction of hydroxyl, radical-containing minerals such as serpentine. It is in depths of more than 100 kilometers that the last hydroxylated species disappear, what generates the formation of rocks composed entirely of anhydrous minerals. The water released reaches the overlying mantle, decreasing the melting point of the periotites. They melt in a proportion not exceeding 10 to 15%. The geothermal gradient is at that time much stronger than today. The rapid rise in temperature with depth leads to the dehydration and melting of the oceanic plate from 50 kilometers or 30 miles depth. The geothermal gradient decreases. Increasingly frequent interactions occur with the mantle as the oceanic plate melts at increasing depths. The Earth reaches its present size. It is still subject to the colossal energy released during the collision. The materials that compose it melt. The iron, more dense, flows towards the center and allies with nickel. After hundreds of millions of years, this core, which has become a liquid and bubbling nucleus, begins to cool. But this cooling does not take place in a homogeneous way in all the core. The differences in temperature between the outer layer and the center cause convection movements in the fluid, which settle in a gigantic magnetic field, that of the sun. Molten iron is a conductive element. If it is set in motion in a magnetic field, it generates an electric current which in turn creates a magnetic field added to the primitive field. The magnetic field will now protect the Earth from the effects of solar flares. Like a shield, it protects the atmosphere, and subsequently, the first forms of life from meteorological hazards with often devastating effects. The impactors of the proto-Earth, whether Theia, planetesimals, or meteorites, are made of rocks, metals, gases, but also a large quantity of water ice. During impacts, some of the energy released is transmitted to the lighter elements, freeing them from the Earth's attraction. Other impacts release volatile elements on Earth. The solar wind is a devastating and burning wind. It sweeps everywhere in its path. All traces of atmosphere are blown to the depths of the solar system. This hellish wind reaches a temperature of more than 700 degrees Celsius, or 1,290 degrees Fahrenheit. The solar wind dissipates the light elements in the interplanetary medium. It is very intense at that time because the sun turns on itself 3 times faster than today, and its activity is more intense. While the young star burns deuterium to form helium-3, its temperature rises and it expels huge puffs of ionized gas, mainly composed of hydrogen. The young Earth is made of very few light elements because hydrogen and deuterium are concentrated mainly in the sun. As soon as the solar wind calms down, the Earth begins the constitution of a new atmosphere. The dust and pebbles that form the primitive Earth are made of molecules capable of vaporizing like water and silicates. Violent phenomena will come in some time to release them. Due to a lack of oxygen, the ozone layer is not yet formed. The water vapor contained in the atmosphere is therefore photodissociated into hydrogen atoms that escape into space under the effect of UV radiation. The primitive atmosphere contains carbon dioxide and nitrogen in great proportion. In addition, there is methane, sulfur dioxide, ammonia, and hydrochloric acid, a composition identical to that of Venus today. The atmosphere is tinted pink due to methane of volcanic, meteoric, and cometary origin. The planet looks like a real pressure cooker. The water is very hot, around 200 degrees Celsius, or 392 degrees Fahrenheit, and strongly concentrated in salt. The pressure of the primitive atmosphere is dense and loaded with water vapor and carbon dioxide, much higher than the current pressure. The crust that forms on the surface of the Earth prevents heat exchange with the outside and causes a brutal cooling. The water vapor present in the atmosphere condenses and a real deluge falls on the whole surface of the Earth. The latter, still very hot and still bombarded by asteroids, receives precipitation of the order of 4 to 7 millimeters of water per year, i.e., 10 times more than the rain that falls in the current tropical zones. In only 1,000 years, the totality of the oceans is formed. These oceans do not stay in place for long. As soon as an asteroid of more than 5 kilometers, or more than 3 miles in diameter, falls on the Earth, it produces such an energy that it vaporizes all the water in place until then. The bombardment calms down, the atmosphere cools down, and the oceans reform. Until the next impact. Asteroids and comets do not only have negative effects on the arrival of water on Earth, their contents are rich in water and partly join the atmosphere. The Earth is composed of large basaltic plateaus and protocontinents. The gas giant planets are in full migration. The effects of gravitational resonance depopulate the asteroid belt of Jupiter and the proximal zone of the Kuiper belt, with Saturn, Uranus, and Neptune. A redoubling of cometary and meteoric impacts occurs during a few million years. The Moon, Mars, Mercury, and the Earth are violently hit. Their surface is marked by numerous impact craters. Some asteroids impacting the Earth have a diameter larger than the size of France. The shocks are so violent that the energy released is enough to vaporize part of the oceans. This heavy late bombardment changes the appearance of the Earth and reintroduces chemical elements that were no longer present in negligible quantities. The surface is as if sown with new seeds. The possibilities of inorganic and organic transformations that occur in contact with the water of the oceans and the atmosphere are revolutionized. It is an open door to the development of life. The large bombardments leave place to bombardments of smaller bodies. The impacts no longer vaporize the water of the Earth. On the contrary, they supply it. The oceans swell. The carbon dioxide present in the atmosphere dissolves in these primitive oceans and makes them very acid. The silicate minerals are disintegrated. The iron, which is not yet oxidized, is released into the ocean in soluble form and gives it a green-brown color. The landscape becomes rather calm, as if it was preparing to welcome life. The pinkish sky covers a large part of the surface of the Earth. The blue planet is not yet so blue. Volcanic gases rising from the Earth's mantle give rise to chlorine, among other things. Meteorites, especially chondrites, contain molten silicates. It is through these two vectors that the Earth is forged with salt. The lighter elements are found on the surface, where they are eroded and then moved to the sea by water and wind. The oceans finally reach their final volume. The Earth seems to calm down. This was without counting on the heavy crust that is cooled and frozen on the surface, which begins to fragment under its own weight and to melt under the heat of the bowels of the Earth. But this does not prevent life from making a first appearance. Traditionally, a planet becomes habitable as soon as water is stable on the surface. This assumes that life is based on the chemistry of water, but also of carbon. The carbon atom is one of the most favorable for the establishment of bonds and consequently for the formation of longer and more sophisticated molecules with diversified properties. Organic molecules are not stable when the temperature is high. It is necessary to wait until the temperature drops below 150 degrees Celsius or 300 degrees Fahrenheit for life to appear. Life at this time is totally bacterial. The first organic molecules are built by physico-chemical phenomena, such as the evaporation of water, the reaction of water molecules with gases contained in the atmosphere, condensation, and precipitation in rain. The prebiotic soup is then transported to the oceans through water runoff. This soup leads to the formation of a kind of membrane on the surface of the water. Shaken by the current, the membrane breaks up into droplets that enclose other molecules separated from the surrounding environment. The coacervates. Bacteria at this time feed on the chemical transformation of organic molecules present in the aquatic environment. After a certain time, because of a lack of food, they start to eat each other. This first act of predation allows a fundamental step in the natural selection and the improvement of the characteristics, since only the best adapted survive. The coacervate is then like a closed system, and its composition is distinct from that of the solutions that surround it. It still lacks the signature of real cells, since it is devoid of proteins, enzymes, and RNA. The emergence of life is, in a very simplified way, a two-step process involving a purely chemical mechanism, prebiotic chemistry, then a series of complex biogeochemical reactions resulting from the very first manifestations of biological activity. The second stage already belongs to the living world and leads the coacervates to become richer until they reach the stage of protobionts, a kind of capsule delimited by a lipidic membrane which contains an emulsion of organic products, lipids, sugars, and proteins. They are the premises of protocells, are not free, and very dependent on their mineral support. Then, catalysis by enzymes and ribosomes replace the mineral surfaces. A true autotrophic metabolism, which feeds on inorganic products provided by the environment, emerges. The protobionts see their mass increase and manage to divide. The structure becomes more complex and resembles that of bacteria. This is where LUCA is located, the last universal common ancestor from which all life emerges on Earth. It is not the first living organism, but a complex organism already resulting from a long evolution guided by natural selection. LUCA is a non-free cell, very dependent on its mineral support, confined in the micropores of alkaline hydrothermal vents. It presents a metabolism based on redox reactions and is able to reproduce. It cannot feed on pre-existing organic matter. On the other hand, it has enzymes involved in the metabolism of nucleotides and a primordial ribosome that synthesizes proteins. LUCA has a complex cellular structure. As soon as LUCA has been able to synthesize the lipid and protein components of its membranes, it evolves in a prokaryotic living being and sets itself free. The world of bacteria opens up to a whole planet to colonize. Some of them become heterotrophic and release methane and oxygen. In the continental cores and around them, belts of green volcanic rocks with their erosion products are set up. Among these rocks, comatites come from deep magmas generated by extensive melting of more than 20% of the Earth's mantle. This suggests a lot of heat to melt such a large part of the mantle. These mountain ranges that are set up are immediately prey to erosion. This is the phenomenon of orogeny. The tectonic movements of the Earth's crust gradually lead to the formation of a supercontinent called Valbara. A supercontinent is a continental mass that includes several continents. They form in cycles through fragmentation and assembly actions influenced by plate tectonics. The supercontinents block the heat flow from the interior of the Earth, which causes an increase in the heat of the asthenosphere and sometimes the appearance of seismic phenomena on the lithosphere as the formation of volcanoes. The magma that rises and some fragments of the supercontinent spread until it breaks up. The reformation of supercontinents occurs when the fragments meet after having drifted to the surface of the Earth. The supercontinent Valbara is formed by the contraction of two cratons, Capfall and Pilbara. The Cratons are the first mountains of the early Earth. Born from a gigantic volcanic activity, these gigantic peaks ignore earthquakes and reach depths of 200 to 300 kilometers, up to 186 miles. The Capfall Craton covers an area of 1,200,000 square kilometers, or more than 460,000 square miles, in the present Limpopo province of South Africa. Its formation and stabilization is due to the presence of granitic batholiths that thickened and stabilized the continental crust. The Pilbara Craton, on the other hand, is located in the current Pilbara region of Western Australia. These two cratons are the only two preserved continental crusts. Single-celled organisms living in water in colonies, they are the first elements of the food chain capable of using sunlight as an energy source. Cyanobacteria are unicellular and do not have a nucleus. They are composed of two differentiated zones. In the periphery, it is the chromoplasma, which ensures photosynthesis and the functions of respiration and nitrogen fixation. In the center of the cell, the centroplasma contains the DNA. They are most often filamentous and slimy. They synthesize their own food through photosynthesis and produce waste products, including oxygen. Photosynthesis is the best known and most widespread mode of chemical energy production, using light and developed by living beings in order to feed themselves. It is carried out thanks to chlorophyll organic pigments. Photosynthesis comes in two variants, oxygenic and anaxigenic. The latter is the oldest. It concerns only bacteria, such as green bacteria of sulfur, purple bacteria, or heliobacteria, living in aqueous medium, devoid or poor in oxygen, and containing dissolved, reduced sulfur. The active pigments of these bacteria are bacteriochlorophylls. Oxygenic photosynthesis, on the other hand, is performed by cyanobacteria and eukaryotes, such as algae and land plants, which are organisms that feed without assimilating other organisms. Their active pigments are chlorophylls. Photosynthesis belongs to the class of chemical equations of oxidation-reduction. Solar radiation provides the energy for the reaction. The pigments capture the light energy. The core of these pigments is a cyclic chemical structure enclosing a magnesium atom. The chlorophyll pigments absorb, preferably red sunlight, hence their green color, while bacteriochlorophyll pigments have a preference for red light and near infrared. Cyanobacteria populate stromolites, half-living, half-rocky structures formed by a filamentous bacterial gelatin that traps carbon from the air to incorporate it as sediment in the rock. Stromatolites are formed by an amazing process. The first colony of bacteria is smothered under a carpet of stone, hence the name stromatolites, since stroma means carpet in Greek, and lithos means stone. Another colony of bacteria comes to settle on this mineral sheet until forming a rock. The construction of stromatolites is slow, since they gain only 0.4 millimeters per year on average. Their forms can vary according to the depth and the movements of water. The sun shines a pale yellow, almost extinguished, which barely dissipates the darkness that reigns on Earth. In the sky, Black stagnant ash clouds spread, and a sulfur smell fills the atmosphere. Jets of basaltic lava rise into the air, hundreds of meters high before falling back to the Earth's surface. The fissures release plumes of white-blue steam from boiling lava. These lavas contain a high proportion of olivine, silicate of iron and magnesium, a high calcium to aluminum ratio, and an extreme richness in magnesium, up to 30%. The intensity of solar radiation emitted is 20 to 30% lower than today. Comparatively, if the Earth's atmosphere had the same composition as our atmosphere today, the planet would have completely frozen in only a few hundred years. This paradox of the cold sun can be explained by several hypotheses. Even if the sun heats less, life is much less developed. The living organisms did not release much oxygen or use the CO2 to precipitate it into carbonate. The vegetation being non-existent, the roots do not consume the CO2 of silicate rocks. The atmosphere is then 10 to 100 times richer in CO2 than today. Methane, in the absence of oxygen, is not oxidized into CO2 and persists in its original form. It is considerably present in the atmosphere. It is thanks to this large amount of greenhouse gases that the Earth has a temperate climate and that liquid water is present. The first living organisms in the water use the sun's radiation to transform water and CO2 into carbohydrates. This transformation process releases a waste product, oxygen. The latter is very harmful for the living of the time. Some strict, anaerobic organisms see oxygen as a deadly poison. It is not a toxic element by itself, but by the derivatives that it will form in contact with certain other biological substances, with, for example, the superoxide ion or hydrogen peroxide. Aerobic organisms have systems that make these derivatives harmless, but the first living organisms have an increased sensitivity to oxygen. Oxygen does not immediately accumulate in the atmosphere because it is produced by living organisms in the oceans. In reaction with the iron present in the water, it precipitates into iron oxide and thus remains limited to the aquatic environment. After 1 billion years, the iron in the oceans is totally oxidized, and it is then that oxygen gradually reaches the atmosphere. Many organisms succumb when oxygen appears. Some manage to escape by finding shelter in niches devoid of oxygen. Then others are forced to evolve to survive in this environment that becomes hostile and become aerobic. The evolution in aerobic passes at first by enzymes which are satisfied to neutralize the poisons created by oxygen. Then, the cell membrane adapts and appears the first system coupling the consumption of oxygen to the assembly ATP. The organisms become, with time, more and more dependent on oxygen for their energy supply. And finally appear the aerobic bacteria. Succeeding the supercontinent Valbara, the paleocontinent emerges, following successive collisions of different island arcs of volcanic origin. The continental crust is sufficiently developed and significantly modifies the chemical composition of the upper mantle. Magmatic differentiation impoverishes the upper mantle as more and more granitic magmas are extracted from it. The Earth has cooled further, and this causes an increase in mantle viscosity. the angle of subduction is increasing, and if the plate is still melting, the resulting magmas are easily mixed with those from mantle melting. New continental lands continue to form. The temperature of the Earth's bowels cools. The basalt continues to sink and dehydrates at the same time, which prevents it from melting. It's water that rises to the surface moistens part of the mantle, which begins to melt and shape new fragments of continental crust of completely different composition. The masses travel at such a power that they will end up assembling into a new supercontinent. The Pongola Glaciation is the first ice age in Earth's history, beginning 2.9 billion years ago. An ice age is characterized by the existence of at least one ice sheet and is associated with a significant lowering of the global average ocean level. An ice sheet is a continental ice cap formed from snow precipitation covering at least 50,000 square kilometers, or 20,000 square miles, over a maximum thickness of a few kilometers or a few miles. Ice ages are related to plate tectonics. When one or more continents drift to polar conditions, snow accumulates in summer. The orogeny, that is to say, the formation of reliefs, favors the appearance of new fractured rocks in the open air, which can be brought to undergo strong alterations and, consequently, a great consumption of CO2 from the atmosphere, leading to a decrease of the greenhouse effect and the temperature at the surface of the planet. The increase of the albedo, or reflective power of the Earth, generates a runaway phenomenon of glaciation, and once half of the surface of the Earth begins to be frozen in white, nothing can counter a total freeze. This phenomenon leads the Earth to a snowball appearance. $2.7 billion years ago, the formation of a new supercontinent begins, Kennerland. It includes the future parts of Laurentia, Baltica, Western Australia, and Kalahari. A few million years earlier, magmatic outpourings under the ocean begin and reach their highest peak with an eruption of comatites. Volcanic arcs are accompanied by upwelling of rocks from the mantle, followed by orogenic deformation, installation of granitoids, stabilization of the lithosphere, and finally, collision with other cratons. It is by accumulating all these phenomena that the supercontinent Kennerland takes shape above the sea level. $2.5 billion years ago, the phenomenon of plate tectonics will take a turning point in the history of the Earth's geology. Until then, two types of plate movement were operating, horizontal and vertical. The latter is explained by subduction, a geological phenomenon that occurs when rocks have different densities. A massive unit, such as ultrabasic lavas of the comatite type, is placed on a less dense unit, such as the crust, and literally sinks into the latter, involving a movement contrary to diaparism. As a result, less dense rocks move up the sides of the inverted diapir. The subduction creates depressions in the middle of the plates and contributes to the accumulation of sedimentary deposits. At this time, the composition of the mantle evolves and the formation of comatites slows down. The density of the basaltic masses being too low to provoke subduction, vertical tectonics ends, and only horizontal tectonics will last until our time. A heavy and unbreathable atmosphere reigns on the Earth. The planet is in a transition phase during which the methane-producing microorganisms give way to photosynthetic organisms and release oxygen in large proportions. The Earth looks like Saturn's moon, Titan, under a thick orange fog. The intense activity of cyanobacteria releases a large amount of oxygen into the seawater, which then reaches the atmosphere. The chemical evolution of the latter is certainly a major event, but the ecological crisis that follows marks the history of the Earth. The Great Oxidation is similar to a mass extinction that kills most of the organisms existing at the time, for which oxygen was then toxic. Living things build structures based on carbon, or on carbon compounds with a nitrogen group. In both situations, this refers to assemblies of carbon atoms. Organisms that contribute to oxygenation draw their carbon from the CO2 molecules in the atmosphere, and their energy from sunlight. When a reaction of fixation of a carbon atom occurs, it releases a molecule of dioxygen. For cyanobacteria, oxygen is therefore only a toxic waste product. Cyanobacteria, through photosynthesis, release a large amount of oxygen into their environment, which then reaches the atmosphere. The oxygen reacts first with the compounds present on the surface, such as methane, salt, and iron minerals. Then, the latter being at saturation, it begins to accumulate in the atmosphere. The oxygen thus released is a poison for the living organisms present at the time, since they are anaerobic organisms. Many organisms existing on Earth are killed. The survivors, in a first time, develop mechanisms to protect themselves from oxygen. Then, in a second time, the organisms evolve into aerobic organisms. Today, they are the majority, since oxygen has become essential. The increase in oxygen concentration provides a new opportunity for biological diversification and changes in the chemical interactions of rocks, sand, clay, and other geological substrates. Without the widespread availability of oxygen, life was previously limited. The energy available to living organisms is now increasing. As early as 2.4 billion years ago, the Earth enters what will remain one of the longest ice ages in its history. The Huronian glaciation owes its name to sedimentary formations of glacial origin found in North America in the Lake Huron region. The entire surface of the Earth is covered with ice. This sudden change in the climate of the planet is closely linked to the evolution of the composition of the atmosphere that occurred at this time. With the appearance of life and the processes of photosynthesis, prokaryotic bacteria release oxygen in large quantities. This oxygen is able to oxidize the methane in the atmosphere, which reduces its concentration. Methane being a powerful greenhouse gas, its decrease triggers a drop in temperature. At the same time, the CO2 is trapped in the limestones in formation, and its proportion in the atmosphere decreases. The decrease in greenhouse gases causes a global cooling, followed by a succession of ice ages. 2.4 billion years ago, the Sun is 20% less powerful than today, which contributes to the sharp decrease in temperature. It is up to minus 50 degrees Celsius, or minus 52 degrees Fahrenheit, for several tens of thousands of years. The water is frozen, the albedo increases as the icy white areas reflect much more. Cooling and freezing increase. In the heart of the Earth, activity is in full swing. The volcanoes emit CO2, which is stored under the ice. At the slightest opportunity, it is released into the atmosphere, suddenly intensifying the greenhouse effect. Temperatures then rise to the surface. A deglaciation occurs in a few tens of thousands of years. During 300 million years, the processes of glaciation and deglaciation will occur 4 times. Volcanism continues to produce carbon dioxide in significant quantities, and it slowly accumulates in the atmosphere. The greenhouse effect becomes sufficient to warm the planet and melt the ice. The decrease of the albedo accelerates the process, leading abruptly to the passage from an ice age to a tropical climate. At the end of this Huronian glaciation, the retreat of the glaciers triggers a massive erosion that disintegrates the silicates, absorbs the excess CO2, and precipitates it into the oceans in the form of silicates. The continents are denuded, but the decrease in CO2 weakens the greenhouse effect and allows a return to more moderate temperatures. The erosion phenomenon tends to bring the continental crust back to zero level. Everything that is in relief above sea level is eroded, and alluvium is deposited in the marine environment, contributing to sedimentary deposits. Conversely, everything below sea level gradually settles until it rises again. As a result of the accumulation of cratons over larger and larger land masses, the oceans become deeper. Iron, in the form of ferrous ions, is present in the primitive oceans in soluble form and green in color. With the appearance of the first organisms, photosynthesis, and the production of oxygen, the composition of the ocean evolves, and so does the form of oceanic iron. Ferrous iron oxidizes into red ferric iron. In this form, iron is no longer soluble in water. It precipitates and falls to the bottom of the oceans, accumulating in the form of sediment until it becomes rock. During periods of glaciation, which are not very favorable to the development of organisms, the production of oxygen slows down, or even stops. The rock is then adorned with a less red layer, with a ribbon-like appearance, rather gray or greenish. The iron having now precipitated, it does not disturb the ocean, which becomes much clearer. The sunlight penetrates more intensely, and photosynthesis takes place at greater depths. Organisms of a new type appear. Coccoid bacteria taking the form of spherules surrounded by a shell, a kind of plankton living on photosynthesis, called phytoplankton. Taking advantage of a moderate climate, this type of plankton, autotrophic towards carbon, develops at its ease. It gets its energy by photosynthesis. Too small to be visible to the naked eye, it can appear on the surface of the water as a colored expanse if its organisms are present in sufficient quantity. Phytoplankton is a primary producer, since its function is to transform inorganic matter, such as CO2, mineral salts, light or water, into organic matter that will be used by other living organisms. Under the influence of plate tectonics, a supercontinent slowly takes shape 2.2 billion years ago. Columbia, also known as Nuna. This supercontinent was welded together during a long period of orogeny and collisions over 4 million years. It includes most of the Earth's landmass and is estimated to extend 12,900 kilometers, or 8,000 miles, from north to south, and 4,800 kilometers, or 3,000 miles at its widest. Until 1.8 billion years ago, the continental blocks move until they reach their final position. The eastern coast of India is attached to western North America. South Australia is welded to western Canada. The cratonic blocks of South America and West Africa are welded first during the Trans-Amazonian and Hibernian orogenies. 2 million years later, the Capval and Zimbabwe blocks collided along the Limpopo belt. 1 million years later, the final assembly takes place. The North American craton suture, the Kola, Karelia, Volgo-Uralia, and Sarmatia cratons join to form Baltica, a paleocontinent. The Anabar and Aldan cratons connect. The North and South Indian blocks join. And finally, the East and West blocks of the China Craton weld together. Columbia remains a supercontinent until 1.6 billion years ago, when it begins its fragmentation. The oxygen now available becomes a new source of energy, much more efficient than fermentation. The world of living things evolves and becomes more complex. Bacteria learn to use this element, and respiration appears. Oxygen is particularly reactive and allows a better catabolism than in anaerobic conditions. Is it at this moment that cells with a nucleus appear? The subject is still much debated. The oldest microfossil, indisputably Eukaryotic, is dated 1.45 billion years, but recent discoveries have revealed traces of multicellular life that would date back to 2.1 billion years ago. This discovery has not been refuted, but some scientists dispute its interpretation. We will place their appearance here in our chronology. The development of new forms of cells is becoming more and more widespread. These are the eukaryotic cells. The term eukaryote covers all unicellular or multicellular organisms that have a nucleus and organelles such as an endoplasmic reticulum, plastids, and mitochondria. The whole is delimited by membranes. In contrast, prokaryotic cells lack these components. Another element that differentiates eukaryotes and prokaryotes is the structure of their DNA strands. The genetic material of eukaryotes is located in the nucleus in the form of linear strands that are compressed during cell division, the chromosomes. Prokaryotic cells, on the other hand, have only one circular chromosome that forms a loop. Eukaryotic cells are larger, on average 1,000 times larger. The first fossil traces are actriarchs, spherical organic vesicles measuring from 20 to 100 micrometers. These eukaryotes most certainly originated from bacteria and archaea, but the process that led to this evolution is still a mystery. Biologists assume that cell compartmentalization would have appeared as a result of capture and fusion mechanisms between prokaryotes and would have resulted in the formation of a eukaryotic cell. This is why eukaryotic cells are larger than bacteria. In 2008, a profusion of centimetric fossils similar to multi-cell eukaryotic organisms were found in Gabon, near Franceville, while the scientific community thought that this form of life had appeared much later. Black clays from the Franceville Basin, which has not been tectonically deformed or metamorphically affected, have revealed fossils of multicellular organisms. Within rocks belonging to a group of 5 harmoniously stacked formations, nearly 400 fossils were discovered in the black clay layers. These fossils measure from 7 to 120 millimeters in length, from 5 to 70 millimeters in width, and 1 to 10 millimeters in thickness. They can take the form of circular aggregates, pyritized or not. In spite of their flat representation, colonial pluricellular organisms are differentiated from bacterial mats by the presence of steranes, which occur during the transformation of sterols during diagenesis. Sterols are properly related to the biosynthesis of eukaryotes. The presence of these eukaryotes corresponds to a time when the oxygen content was still low, between 0.1 and 1% of the current concentration of the atmosphere. Researchers believe that these are assemblies of cells that communicated with each other and were capable of coordinated movements. At this time, 2.1 billion years ago, multicellular organisms were not at their peak, but they were making a quiet entrance into the world of life. They will spread and diversify more widely a little later. The appearance of eukaryotic cells is jointly linked to the appearance of compartmentalization within the cells themselves. It is expressed by the presence inside the cell of various organelles and a nucleus that imprisons the genetic material. 2 billion years ago, the endosymbiosis of a protobacterium would have allowed the appearance of a particular organelle, the mitochondrion. During their evolution, cells meet and interactions occur. Some cells absorb other cells. If digestion does not occur, the ingested organism reproduces within the host cell. Over time, the bacterium no longer has autonomy and becomes an organelle. Endosymbiosis is defined by this type of association, when one of the partners lives inside the other and provides a benefit to all the cells. Anaerobic cells with a nucleus would have ingested bacteria capable of transforming the energy of certain molecules into energy that can be used for other reactions. Some of these absorbed bacteria become machines, allowing the production of energy for the cells, the mitochondria. These are the respiratory and energy centers of the cells. From 1.8 billion years ago, and for a period of 1 billion years, the Earth is in a period of relative calm. Its tectonic activity is stable, as is its atmospheric environment. Biological evolution is slow due to low oxygen levels. No glaciations have been recorded, no major catastrophes, no major innovations. This period is called the Boring Period, and translated by the Boring Billion. This appellation can be considered as unfair, since the planet will undergo significant events in the billion years that will follow. This period would have been marked by a particular oceanic regime based on chemistry, designated by the expression of Intermediate Ocean or Canfield Ocean, named after the scientist who postulated the existence of this ocean. During the Great Oxidation, the oxygen produced oxidizes certain chemical elements present in the ocean, such as iron, but it is not present in sufficient quantity to oxygenate the entire aquatic environment. In parallel, the alteration and oxidation of continental rocks are accentuated by the formation of supercontinents and the oxygenation of the atmosphere. Sulfate ions are then introduced in mass into the oceans. The waters of the planet during 1 billion years are enriched in sulfur, but contain almost no iron and very little oxygen. This new composition will have two effects on marine microbial organisms. On the one hand, bacteria that are highly dependent on sulfur will proliferate, such as purple and green sulfur bacteria and sulfate-reducing bacteria. On the other hand, living organisms have difficulty synthesizing the ammonia they need, because this synthesis is intimately linked to an enzyme containing iron, of which the Canfield Ocean has little. Their development is consequently slowed down. A continental rift forms 1.6 billion years ago. It extends along the western margin of Laurentia, eastern India, the southern margin of Baltica, the northwestern margin of South Africa, and the northern margin of the North China Block. Strong magmatic activity accompanied this upheaval. The total fragmentation of the continent was spread over 300 to 400 million years. The great story of the cells continues. 500 million years after the cells were equipped with organelles allowing the production of energy, a new organelle essential in the functioning of the plant cells will make its appearance: the chloroplast. Like mitochondria, chloroplasts are the result of endosymbiosis and capture the light that causes photosynthesis. It is by feeding on external elements that cells with a nucleus ingest certain photosynthetic bacteria, and that arrangements intervene at the level of the symbiotic partners. Cyanobacteria are photosynthetic microorganisms that can capture light thanks to pigments, and are able to synthesize their own organic matter. Gene transfers take place between the nucleus cell and the ingested bacterium. The resulting cell consists of the genetic material of its nucleus, that of its mitochondria, and that of the new elements. It becomes a self-sufficient cell. Until then, organisms reproduce by simple division. From one generation to another, they remain almost identical to themselves. The biosphere will evolve considerably with the appearance of a new mode of reproduction: sexual reproduction. It is a great step in the evolution of the living. This complex form of sexuality is called meiosis. A normal cell containing two sets of chromosomes divides into specialized cells whose nuclei contain only one set of chromosomes. Each cell must then find a complementary partner to fuse and reconstitute a cell that will then have all the chromosomes. Fertilization consists of the fusion of the male and female sex cells, and thus the reunion of two sets of chromosomes. Such a mixing of genes will generate an enormous diversity of individuals and the appearance of new species. Plate tectonics continues to turn the continents upside down. 1.1 billion years ago, under its influence, the continental masses regrouped and formed Rodinia. The eastern coast of the current United States is close to the western coast of the current South America, and our current Antarctica and Australia are adjacent to the west coast of the United States. A planet that looked very different from what we see today. The supercontinent Rodinia is surrounded by the ocean, Microbial. It extends from 60 degrees north latitude to the South Pole. Inside its seam zones, Rodinia has a huge rust-colored plain on which sands accumulate. The surface of the Earth is completely deserted. The life remains confined to the aquatic environment, since the atmosphere contains only 5% of the concentration of oxygen that we know today. Situation which does not allow the development of the layer of ozone, which protects the surface of the Earth of the ultraviolet rays. The surface temperature is estimated at an average of 10 degrees Celsius, or almost 50 degrees Fahrenheit. The sun is 6% weaker than today, and its rays are not as powerful. A day lasts at that time less than 22 hours, and a year has 13 months. The formation of a supercontinent like Rodinia acts like a lid on the planet. This cover evacuates the heat from the Earth only by the phenomenon of conduction, which is not very efficient. The heat that is not evacuated accumulates and causes the temperature of the upper mantle and the lower crust to rise. The central parts of the continent become hotter. As a result, the density of the rocks decreases. They rise to the surface and form huge domes. The crust is stretched and becomes thinner. Cracks appear, from which magmatic rocks in fusion pour out. The volcanic activity intensifies. A superdome formed 850 million years ago cracks 1 million years later. Lava takes place in the trenches created. As they move apart, water invades the trenches, and new oceans are formed. New conditions were created that would allow life to find refuge from the harsh events it would endure over the next few million years. About 750 million years ago, Rodinia broke up. At that time, the supercontinent is centered on the equator. Subjected to the effect of hotspots, the Earth's crust is crossed by enormous quantities of lava that pierce it like spears. Oceans and inlets open up, increasing the amount of water vapor in the atmosphere. Heavy rains fall on the Earth and subject the fractured continental rocks to a strong alteration. This phenomenon consumes a lot of CO2. The size of the coastline grows. Marine and coastal organisms proliferate, using massive amounts of carbon dioxide from the atmosphere. Lava flows caused by the breakup of the supercontinent form basaltic surfaces on the surface of continental blocks. Under the effect of humidity, these basaltic surfaces erode and consume large quantities of CO2. Deprived little by little of carbon dioxide, the greenhouse effect is reduced. The Earth appears calm. The oceanic ripples are not very active, but the average temperature at the surface of the planet decreases considerably, to the point that freeze-ups occur. The Earth becomes snowball again. The ground temperature averages between minus 40 degrees Celsius and minus 50 degrees Celsius, i.e., between minus 40 degrees Fahrenheit and minus 58 degrees Fahrenheit. When night falls, it drops to between minus 80 degrees Celsius and minus 100 degrees Celsius. That is, between minus 112 degrees Fahrenheit and minus 148 degrees Fahrenheit. The sun is about 6% less powerful than today. It shines less intensely and produces less energy. Its luminosity is low. A climate of desolation reigns on the Earth. The air is dry and cold, unbreathable because of its low oxygen content. No more liquid water circulates, except at the base of the glaciers, which puts the water cycle at risk. The freeze-ups follow one another and get out of control in a real vicious circle. The icy surfaces get bigger and reflect more and more sunlight into space. This is the famous albedo effect. The temperature at the surface of the Earth decreases even more. The thickness of the ocean ice reaches more than 1 kilometer. Like a large pearly mattress, the ice nevertheless leaves gigantic crevices in some places in which organisms are resisting. The fauna and flora undergo extreme conditions, but also find refuge at the bottom of the oceans within a thin strip of ice-free water that has been able to survive thanks to the extraordinary properties of water. As water cools, its density increases, and below 4 degrees Celsius, or 39 degrees Fahrenheit, its volume also increases, even after it freezes. During the Ice Age, the water begins to cool at the surface. It becomes denser, and a current is created. The cold water flows and homogenizes the temperature over the entire depth. As soon as the temperature drops below 4 degrees Celsius, or 39 degrees Fahrenheit, the surface water becomes less dense and remains at the surface. This is how the ice form creates the thermal shield that prevents the seafloor from freezing and allows organisms to survive. The Varanger glaciation would have benefited the diversification of life, according to some research. At the end of the glaciation, when the ice melts, the erosion of the continents leads to the release of large quantities of phosphorus. This phosphorus is dissolved in the oceans and encourages the proliferation of phytoplankton. Oxygen is released into the atmosphere, which facilitates the appearance of new organisms. As in most ice ages, the Earth's core remains active throughout the Varanger glaciation. Emissions of CO2-rich volcanic gases do not stop, so after 1 million years, the Earth's thick ice cover begins to melt. Greenhouse gases take their place in the atmosphere, since nothing else transforms them. There is no more alteration of rocks or biological consumption. The ice melts, and the surface of the Earth warms up at a crazy rate, from -50 degrees Celsius or -58 degrees Fahrenheit to 50 degrees Celsius, or more than 122 degrees Fahrenheit. Scientists assume that this sudden warming is due to a sudden and massive release of large quantities of gas accumulated under the ice. The planet is freezing itself from the snowball that was imprisoning it. During its fragmentation, the supercontinent Rodinia separated into 2 parts. An ocean was born between the two, Panthalassa. North America moved southwards towards the South Pole. The northern half of Rodinia, under the pressure of the ocean, turned on itself, making its eastern part go up to the north, much more than its western part. Between these 2 parts, a third continental block extends, the Congo Craton. A few million years later, these 3 continents came together to form a new supercontinent called Pannotia, which remained in place until 540 million years ago. The collision gives birth to a mountain chain, the Pan-African orogeny, and welds the various African cratons. This new continental block formed is of remarkable stability, so much so that it will later give birth to Africa. Life is confined to water. Before 600 million years, nothing protects it from the ultraviolet rays emitted by the sun. The molecules of living matter are photosensitive and can be destroyed if they are confronted with certain radiations like ultraviolet rays. Ozone has 3 oxygen atoms. This molecule is formed following several chemical transformations involving nitrogen oxides under the effect of the sun's ultraviolet rays. Ozone then accumulates in the stratosphere. For this phenomenon to occur, oxygen must be sufficiently abundant in the atmosphere. It is at this time that the ozone layer begins to form, present at 90% of the current amount. It will reach its totality 200 million years later. Ozone is naturally limited and balanced since it is constantly created and removed by the activity of ultraviolet light and oxygen. It absorbs a large part of the ultraviolet rays and protects living organisms from their harmful effects. With the formation of the ozone layer, marine diversity will explode. The Earth has just suffered climatic catastrophes, but the biosphere is hanging on. As the ice melts, the ocean reappears and life prepares to reclaim the waters of this new Earth. The deglaciations cause a strong continental erosion and consequently an important sedimentation of the littoral zones. The sediments contain various organic matter emanating from the multiplication of organisms present in the coastal waters. This organic matter is transformed into carbon. The sequestration of CO2 from the atmosphere by the sediments supplies oxygen to the oceans and then to the atmosphere. The living beings have now extraordinary possibilities of diversification. Thus, the famous fauna of world extension, named fauna of Ediacaran, makes appear large, strange animals, still entirely deprived of rigid parts. This fauna is found on all the continents, which means that it is not a question of a regrouping of organisms in only one place subjected to very specific conditions. This fauna developed on the whole surface of the Earth, which represents a great step in the development of life. Ediacarans are among the most intriguing fossil groups ever discovered. They are unlike any other living creature. With a soft body, no mineralized skeleton, they have a padded appearance. They take various forms, going from the round like the jellyfish to a radial, triradial, or bilateral symmetry to that of a disc with a head. The Ediacaran fauna nests on most continents, which is quite rare for organisms living on and in the seafloor. As the Earth is recovering from an ice age, the oceans are still cold at this time, and the climate zones have not yet recovered. Ediacarans measure from a few centimeters to more than 2 meters in length for the largest. They are the first fauna of large organisms to have developed, or at least to have fossilized. Some live under the sands of the seafloor and can move and push themselves when sediment is dumped on them. Others develop tubes connected to their bodies to fill them with sand. The fauna of Ediacaran has about 100 species and a dozen groups and many organizational plans. The main groups include discoid forms, mainly simple flattened discs. They look like jellyfish, but are really quite different since they live in dense populations on the seafloor. The mossonites also have discoid forms. They measure about 12 centimeters or 5 inches in diameter, and their bodies have tubes or pockets filled with sand. The bodies of vendobionts, like Rangia, are bag-shaped with bilateral symmetry. They live buried in the sand. One of the best-known families of the Ediacaran fauna are the Dickinsonids, including Dickinsonia. They have the shape of a small, flat oval disc, and they evolve into a ribbon by widening and flattening. A longitudinal axis divides their ribbon into 2 parts, with thin segments on each side. The Dickinsonia can measure from a few millimeters to 1.40 meters or 5 feet in length. They do not have a digestive system, nor a mouth and anus. They feed by consuming bacterial films that cover the seafloor. Yorgoids and vendobiodes also have segmented and discoid bodies, with one end different from the other. They are able to crawl on the sediments. The Charnia group have fronds. It is attached to the sedimentary surface and stands on the seafloor. Most of these organisms measure about 10 centimeters, but some reach up to 2 meters. If there are enough of them in close proximity to each other, they form small thickets on the seafloor. The Trilobosarians are a remarkable group of Ediacarans. They have a body with triradial symmetry, including 3 lobes twisted in a spiral, which remains rare in this population. They are discoid and present surprising and unknown details that really differentiate them from other living forms. They are mostly covered
with branched radial grooves. Their diameter varies between 0, 3, and 5 centimeters, that is to say, almost 2 inches for the biggest specimens. The Ediacaran fauna cannot be mentioned without referring to the microbial mats that cover many sedimentary surfaces. They are at the base of the food chain for some Ediacarans, while others simply filter microorganisms from the seawater. The fauna of Ediacaran flourished until 542 million years ago. It represents a first diversification quickly aborted of the pluricellular animals. The cause of its disappearance still remains mysterious today. Several hypotheses are proposed, such as a general disturbance of the environment, a biotic replacement, following the appearance of new species of Cambrian type, or a change of polarity of the Earth's magnetic field, which would have reduced the ozone layer, and thus increased the ultraviolet radiation on the surface of the Earth. Four large continents form the landscape of the Earth, following the breakup of Rodinia. They are located mainly in the southern hemisphere. Laurentia represents the ancient lands of North America and Greenland. Siberia is located east of Laurentia. Baltica, composed of Scandinavia and western Russia, is located southeast of Laurentia. The last continental block, not the least, which stretches from the South Pole beyond the equator, is Gondwana. This last piece includes the ancient terrains of South America, Africa, Australia, India, and Antarctica. The Lapitous Ocean flows through the middle of Baltica and Laurentia. The emerged lands are still uninhabited and without life. They undergo erosion. The sea spreads over shallow depths and covers continental shelves. This creates ideal conditions for life to develop. The metazoans are quite numerous, even if they are not varied and have a microscopic size between 1 and 5 millimeters. Metazoans are the group of organisms that qualify animals. They are multicellular, since they contain several differentiated cells. Their cells have a nucleus and organelles, such as mitochondria. They feed organically. In parallel with the tectonic events of this period, life begins a profound evolution and a decisive turning point in the evolution of life on Earth. 541 million years ago, it is the Cambrian faunal explosion. Some scientists call it the Big Bang of life. It results in a gigantic renewal of the fauna. New plans of animal organization appear, accompanied by new genera and new species. Nearly half of the current phyla are identified at the beginning of the explosion. The Cambrian fauna is composed of epibenthic animals which live on the seafloor. They are partly burrowers and pelagic and have new ways of feeding. The food chains are more complex than those of the Ediacaran fauna. The reasons for this explosion are still debated today, but an interesting hypothesis tends to be validated. A rapid and important slip of the Earth in relation to its axis of rotation would have moved Laurentia and parts of Gondwana from high to low latitudes. This event would have been followed by marine transgressions. The temperate coastlines of the continents and the increase in shallow, submerged continental surfaces would have allowed life to proliferate, and consequently would have led to an exceptional increase in diversity. During this period, which lasted until 485 million years ago, 3 different faunas succeeded each other: the Tomat fauna, the Chengjiang fauna, and the Burgess fauna. The Tomat fauna is characterized by small and very diversified fossils measuring between 1 and 3 millimeters long. They belong to sponges, mollusks, and other annelids. They exhibit calcareous, siliceous, or phosphate shells. This fauna represents a major phase in the diversification of multicellular animals with shells and in the mineralization of skeletons. It is considered a key fauna, even if it only lasted a few million years. Like the Ediacaran fauna, the Tomaschian fauna is recognized worldwide. It includes some modern-looking organisms, but most are made of tiny blades, needles, caps, tubes, or domes. Called the small shell fauna by paleontologists, it is mostly made up of the beginnings of shells, small scattered fragments. It is not confirmed today that these first fragments of shells would have represented the beginnings of an evolution of animals with shell, or that they would have remained single organisms which disappeared very quickly. The Tomat fauna marks the appearance of a group of organisms belonging to the sponge phylum, the Archaeocyaths. They are the first bioconstructors in association with calcifying microbial organisms to raise organic masses up to 2 meters or 6 feet in height and several meters or feet in diameter on the seafloor. These masses are the pioneers of the complex reef ecosystem that will develop a few million years later. Archaeocyaths consist of a calyx formed by 2 nested porous cones. Their skeletal parts are made of magnesian calcite. They are sessile, benthic, and filter feeders. In order to ensure their feeding, they are found in habitats subjected to a current and a strong turbidity, ensuring them a supply of nutriments. They do not have great capacities of adaptation and have constraints of temperature, salinity of the water, and depth. The fauna of Chengjiang is represented by at least 16 different phyla and about 196 species with a strong predominance, about 40% of arthropods. Vertebrate and invertebrate organisms are present in great variety. These fossils were covered by a layer corresponding to the mud of a warm and shallow sea, which allowed a remarkable preservation of the anatomy of their tissues, whether hard or soft, as well as the elements of their digestive and nervous systems. The groups recorded are extremely varied: sponges, algae, cnidarians, annelids, numerous bilaterians, as well as at least 4 groups of vertebrates. Hycuithus is the first true vertebrate identified as such. It could be classified as the first vertebrate fish, but it does not have all the characteristics to be included in that time, like slimy worms or big arthropods. It has a series of W-shaped muscles called myotomes that are attached to its bones located in the dorsal region. This allows it to propel itself easily and to have better control of its movements. Thanks to the myotomes and the supporting skeleton, its head is different. The skeleton begins to play a protective role in addition to its supporting role. It is made up of bones and not cartilage. Hycuithus has adapted and evolved. With time, also enables him to aspire small prey like worms. Active predator, it is a good swimmer, even if until today. It is the proof of a very complex and diversified invertebrate fauna. It measures between 4.3 and 7 centimeters, up to 3 inches. Its body is soft and segmented. On its head we count 5 eyes. It has a long and mobile proboscis, like a trunk, attribute exclusively seen on this animal, which makes it an extraordinary creature. This proboscis folds up its mouth and is equipped with prehensile spines being used to catch its prey. It searches the sediments to find its food. Thanks to its lateral lobes, it can survey the seabed and move around, and thanks to its proboscis, it recovers its food in the tunnels dug by worms or bivalves. The Burgess fauna is dated to 505 million years ago. Compared to the two other faunas, it constitutes a real explosion, in the literal sense of the term, since it sees the appearance of a quantity of new, complex, and varied organisms. It is the fauna of the Big Bang of life. It was discovered in a site in the Rocky Mountains in Canada. It was found to be in continuity with the Chengjiang fauna and is in very good condition. Burgess remained for a long time the only site giving access to the Cambrian fauna. The fossils were discovered in shales from a marl limestone formation. During sudden underwater avalanches, the organisms were buried under a mudflow. Their good state of preservation is explained by the fact that the mud carried with it all the small creatures on the seafloor. It trapped them where there was neither oxygen to decompose them nor predators to devour them. The extremely fine sediments insinuated themselves everywhere, around and inside the organisms. The small corpses were trapped whole under a sludge that gradually solidified into shale. The Rocky Mountains were formed, and the Earth's convulsions lifted and crumpled large parts of the marine sediments. Some layers were crushed, leaving no sign of life, but one layer remained intact. The places where the fossils of this fauna have been found suggest that these animals live on slopes of accumulated mud at the foot of a large imposing wall, positioned almost vertically. 120 genera make up the Burgess fauna, of which 33 are ordinary organisms belonging to currently known phyla, and which have an exoskeleton. Sponges, brachiopods, trilobites, algae, mollusks, and echinoderms are among them. 87 genera of soft-bodied organisms are also listed. This fauna is very original. Some organisms will not be found in the future geological times. They will mark only the Burgess fauna. At that time, there are 24 fundamental types of organization in arthropods, and only 4 will persist. Arthropods have a segmented body with legs or appendages. This division into segments appears from the embryonic life. A rigid carapace constitutes their exoskeleton, made in most cases of chitin. Thanks to molts, they regularly change their external exoskeleton, which allows them to gain in size, to acquire new organs, or even to change their shape. Arthropods are a worldwide group that can adapt to the different types of environment around them. Several species of arthropods evolved 500 million years ago. Branchiocyrus is a kind of arthropod with a bivalve shell that hides 2/3 of its body. It measures between 8 and 9 centimeters long and has a very segmented trunk, at least 40 segments of annular shape. This animal is provided with a pair of small antennas and a pair of clawed appendages. It is an active swimmer and uses its appendages to bring food to its mouth. Marella is a species of arthropod that is part of the soft-bodied fauna. It has a cephalic shield and a body made of about 20 segments. 2 pairs of unirammed appendages decorate its head. Its cephalic shield has a horseshoe shape and is adorned with 2 kinds of horns, curved extensions that run along the body for most of its length. The rest of the body of Marella is thin. This species is able to undulate its body in all directions. Trilobites are among the best-known arthropods. On average, they measure between 2 and 7 centimeters, or about 2 inches, but some individuals were up to 70 centimeters long. That is more than 25 inches long. They are present in abundance on the seafloor and are among the most diversified. There are nearly 19,000 species that have been detailed to date. Their specific anatomy places trilobites in a very special group. Their trilobation is indeed unusual. They have a median lobe and 2 lateral lobes which are protected by an exoskeleton. The trilobites live only in water, and more precisely, on or in the substrate, which constitutes the bottom of the sea. Some forms of trilobites evolve, however, in pelagic, that is to say, that they live and move in a body of water. To this end, their exoskeleton is modified so that the body has more stability, and they also have a better view. Trilobites live in groups. They feed on worms and any other benthic invertebrate. Sydnea measures between 5 and 13 centimeters in length, about 5 inches. Its structure is singular. Its head has only a pair of eyes and a pair of antennas, but they are the first creatures on our planet with advanced eyes. On their so-called compound eyes, each facet has its crystalline lens of calcite oriented to perceive the maximum amount of light possible. In only one eye, 15,000 elements are contained. The trilobites have a practically hemispherical field of vision. The segments of their thorax carry a pair of solid appendices. This carnivorous animal walks on the seafloor in search of food, mainly small trilobites and hyoliths. The trilobites will spread in the ocean and divide into a large number of species. Among the phylum of annelids, one animal stands out for its unusual structure. It is Hallucigenia. With a long and slender body like that of a worm, the animal has 7 pairs of tentacles that end in claws on one side and join spines on the other. It moves on its tentacles, and its spines are erected on its back. The 3 pairs of fine tentacles at the level of its head are used to sort out its food and to orient itself like antennas. Sponges also adorn the Cambrian seabed. These animals are equipped with an aquifer system that allows the circulation of water. Sponges are adorned with 2 layers of cells. On the outside, the pinacoderm, and on the inside, the choanoderm. In the middle of the 2 layers, mobile cells circulate in a cellular matrix, mainly composed of collagen. Sponges adapt to fresh or marine waters. They can settle up to 5,000 meters deep. They are great consumers of bacteria, organic debris, and algae. They feed by filtering the water. The water, which is filled with particles, enters through the pores of the sponge. Large particles are absorbed, organic particles are digested, and inorganic particles are rejected through the pores. Sponges are very strong. Even if they are crushed or torn off, their cells reassemble and regenerate. They are also resistant to changes in acidity and survive during climatic warming and ocean acidification. Echinoderms are a very diverse group of marine animals that have the particularity of having a central symmetry and a star shape, called pentaradial. They have a skeleton made of bony plates and have a water system like sponges. To function, the body of echinoderms uses hydrostatic principles. Their feet are like small extensions, provided with suction cups, maintained inflated by the pressure of water. The water circuit necessary to the functioning of this system is independent. The water enters through a hole drilled in a ring around the mouth, and it spreads throughout the body through internal channels. One of the most widespread species of echinoderms is the sea lily. In its flowering stem form, the sea lily has a 3-part body, a root system with spikes that allows it to attach to the seafloor, a stem that can be up to 1.50 meters or 5 feet long, with a base that is stiffer than the top, and a calyx covering the vital organs topped by a dozen mobile, feathery-looking arms. To feed, the sea lily spreads its arms and captures planktonic particles. The sea lily is spared by predators because most of its body is calcified. It is able to regenerate itself. It lives in shallow waters attached to hard bottoms, such as clusters of shells. The last of the Burgess fauna that we will talk about are the brachiopods. They are present in great numbers and in a very diversified way. Their shell is composed of two valves, a ventral valve and a dorsal valve. Inside, there is a brachial skeleton from which filaments spring up that capture plankton and lead it to the mouth. Brachiopods live attached to their substrate. There are 12,000 species of brachiopods at this time, including Lingulella. Buried in the sand and mud of estuaries, this species looks like a long worm, with two horny valves at one end. Its structure is complex. Its tentacles are covered with vibrating cilia that cause water currents. These cilia are loaded with food particles, which are then led to the mouth. The tentacles have another important function. They absorb oxygen and act as gills to allow the animal to breathe. The valves protect the tissues and concentrate the water currents. Over the next 100 million years, brachiopods improved their valves considerably. All these elements of the ecosystem are in balance with each other, but future events will disrupt their peaceful life. It is now 485 million years ago, and life is about to emerge. The area around a volcano after an eruption is among the most barren of lands. The black lava flows that previously rolled down the flanks are now frozen. Steam flies between the blocks and yellow sulfur, encrusting the mouths of the chimneys. Further away, everything is quiet. However, the continents are not immobile. They continue to drift, animated by the convection currents of the Earth's mantle. The continental surface is empty like a great desert. No bushes to protect from the wind, nor greenery to brighten up the black surface of the ashes. Although the evolution of the Earth has allowed the development of life in the ocean, the dry land remains barren. Plants resembling lichens and our current mosses begin to settle on land. These first colonizers reach the rocks and cling to all their irregularities. They then develop spikes. The water not yet circulating in their tissue, they let themselves dry out until rains fall and they rehydrate completely. Other plants resist drying out by developing an impermeable cuticle that reduces water loss through openings that allow gas exchange. For the moment, these plants have no leaves. They are lying or standing. They colonize in abundance the aerial and mineral environment and provide microorganisms with a raw material that will lead to the formation of the first vegetable soils. A wide variety of organisms can now try their hand at these new conditions. This conquest of a new environment is only the beginning of a large colonization which will radically change the aspect of the Earth.
The Earth has so far offered a desolate landscape. Lava flows from volcanoes have rolled down its sides. Now immobile, they still crackle but slowly freeze. Lakes of yellow, blue, or gray mud are bubbling. The heat coming from the bowels of the Earth bursts on the surface of these muds in thick bubbles. When the first volcanoes appear on the surface of the Earth, they contract in extraordinarily violent eruptions before cooling down and building gigantic mountains made of ash and lava. Over the years, these rocks evolve into mud and clay under the action of wind and rain. The debris is carried away by torrents and carried to the sea, then accumulates and forms shales and sandstones, At the same time, the continents continuously in motion are moving. When they meet, the surrounding sediments are dragged along and compressed to form new mountain ranges. As geological cycles progress, volcanoes erupt, then die out, and life proliferates on the seafloor. As for the dry land, it remains sterile, until the day when 4 large continents remain: Laurentia, Baltica, Siberia, and Gondwana. They are drifting. Facing Laurentia, the margin of Gondwana begins to crumble into several small continents. The first individualize is Avalonia. Its distance diminishes the Lapitous Ocean and opens the Rick Ocean. This is the beginning of the Caledonian orogeny. From 485 million years, very primitive plants, resulting from association between algae and fungi, come out of the water to settle on rocks in the open air. Adorning with green the edges of the beaches and the rocks, these plants cannot extend. As soon as they go beyond the areas moistened by the spray, they dry out and do not survive. Water does not circulate in their tissues. To face the desiccation, they develop capacities of return to life. They dry out completely and rehydrate themselves as soon as the first rains come to return to life. Other plants develop an impermeable waxy film that reduces their water loss. For the moment, the plants have simple forms with a very primitive vascularization and have no leaves. They are intimately linked to the aquatic environment for their reproduction process. Mosses are among the first plants to colonize dry land. They remain low to the ground, continuously established near the shore, but manage to disperse somewhat. Mosses do not have roots. Their gas exchanges are carried out thanks to stomata, openings which open and close in order to regulate the flow. Deprived of lignin, the tegills of mosses are condemned to remain soft and have no consistency. They only rise when they grow tightly together. Mosses function like sponges. Their water-filled cells are partitioned, and they must stay close to the ground to draw water. Mosses release spores, reproductive corpuscles, onto moist soil, which will allow them to reproduce, either asexually or sexually, on an alternating basis. Sexual reproduction is important in the history of evolution because it requires the meeting and fusion of 2 sex cells that need a liquid medium to move and join. Each ovum is attached to the top of the stem, while the spermatozoa are released into the water and move until they reach it and fertilize it. The ovule germinates, attached to its mother plant, and produces the asexual generation. A small stem with a capsule at the top with many spores. As soon as the air becomes dry, the capsule grows, opens, and releases the spores, which are scattered by the wind. Spores that fall on moist soil will develop into young plants. Liverworts have appeared alongside mosses. These plants do not have roots, but rhizoids, filaments which fix them solidly to the substrate without allowing them to absorb nutritive elements. The gas exchanges are done thanks to pores, openings which remain fixed. The colonization of dry land by plants is a fundamental step in the history of the Earth because it results in a significant increase in oxygen in the atmosphere and a decrease in CO2. Plants use photosynthesis to produce their own organic matter. They draw on solar energy, extract atmospheric CO2, and release oxygen. The Earth's atmosphere is marked by a second significant increase in its oxygen concentration, the first being the Great Oxidation Crisis. The proliferation of plants on land is the origin of the formation of soils. Before, the surface of the Earth was only mineral, consisting of bare rocks and grains, such as sand and silt. The first plants to occupy the soil emerged, then died and decomposed. Litter and humus were formed, and as a result, new environments were created for the development of other plants, fungi, and animals. The mosses and liverworts spread and form vast green carpets with the appearance of real Lilliputian forests that, starting from the seashore, extend towards the interior of the land. The mainland appears lifeless. The rocky ground is now covered here and there with mosses. The temperature is about 30 degrees Celsius, or 86 degrees Fahrenheit. The ozone layer is thickening, and ultraviolet rays are only partially filtered. For the living, it is better to stay underwater. The sea level is high. Gondwana is located in equatorial latitudes and is moving towards the South Pole. It is partially covered by shallow seas. Its proximity to the pole starts a drop in temperature that will gradually lead to the appearance of glaciers. But during this time, life is in full swing. Oxygen levels reach 2% of the current atmosphere, a level so low that the living beings of our time would have great difficulty in breathing. The gigantic Panthalassa Ocean covers most of the planet. It is at this time that the marine biodiversity will increase in an exceptional way. It is the great biodiversification of the Ordovician. 490 million years ago, the Earth's atmosphere was rich in CO2. The greenhouse effect induced by this gas maintained warm temperatures. Ocean temperatures could rise to 45 degrees Celsius, or 113 degrees Fahrenheit, which is not very favorable to a high level of dissolved oxygen. The development of life helps to absorb and fix CO2 through the process of photosynthesis. 30 million years later, the land cooled, and this cooling was accompanied by an increase in biodiversity. The number of genera of marine animals quadrupled. The ocean becomes an aquatic paradise, populated by creatures, all more extraordinary than the others. The water of the ocean is enriched in oxygen, which allows some animals to reach considerable sizes. The development of plankton favors the appearance of a great diversity of benthic fauna. Organisms secreting carbonate-based shells appear in mass, such as cephalopods, crinoids, and articulated brachiopods. Coral reefs develop. The first ectoprocts arrive, and mollusks become common. In the middle of these warm and sunny waters, trilobites of 60 centimeters or 24 inches long wander in search of food, plankton, pieces of algae, or animal droppings, sucking up the ocean floor. They share the waters with a brand new roommate, the Astraspis, a primitive species of fish. Despite its small size, which does not exceed 15 centimeters or 6 inches, the Astraspis has for the first time a primitive backbone and the existence of a bony carapace that protects the spine. It is the ancestor of the future living beings of the planet Earth. Astraspis is not a predator. It feeds on algae and microbes. It does not yet have a jaw, but sucks its food. It is not a very good swimmer. Its only means of defense is an armor covering its head and part of its body. Its sight allows it to distinguish shadows, and its skin reflects the vibrations of its possible predators. Faced with the Astraspis, the Orthoceras reigns over the ocean as a fearsome killer. Being able to measure up to 6 meters or 20 feet long, and weighing more than 1 kilogram or more than 2 pounds, this ruthless and insatiable carnivore is similar to the great white shark as it is feared. It has a cone-shaped shell that contains an air-filled chamber which allows it to float. Although it is feared by many species, the Eurypterid or giant sea scorpion is not afraid of it, and they regularly clash. The Eurypterid is the largest arthropod. It measures 2 meters or 6 feet long and weighs up to 130 kilograms or 290 pounds. A cross between a lobster and a monstrous scorpion, it has a needle-like jointed tail. Its giant claws are sharp and allow it to crush and cut its prey. As a true predator, it feeds on invertebrates, mollusks, and primitive fish. Arthropods, small animals of only a few centimeters or a few inches, covered with a very thin carapace, appeared already a few million years ago. During the great biodiversification of the Ordovician, their shells became harder, and they evolved into gigantic marine animals. The horseshoe crab, which was later considered a living fossil, is an aquatic animal that looks somewhat like a crab. It has a gray, brown, or black carapace. It measures up to 70 centimeters or 30 inches and weighs 5 kilograms, almost 11 pounds. Its head, very broad and rounded, contains 2 small eyes at its top. Its abdomen has 6 pairs of sharp spines and ends with a sting. With its 5 pairs of legs arranged around its mouth, it seizes food. The horseshoe crab has a particularity. It has blue blood. It is the copper contained in its blood which gives it this so particular color, whereas the blood of the vertebrates contains iron. It lives mainly on sandy or muddy bottoms of superficial oceanic waters. The horseshoe crab feeds on mollusks, small fish, worms, crustaceans. The corals land in this flourishing ecosystem. They slowly colonize the oceans and build up into coral reefs. The coral is a small animal that looks more like a plant organism, like a flowering tree. It lives attached to rocks, near the surface of warm waters or at the bottom of the sea, sometimes even in cold waters. Corals make a common skeleton, which becomes the basis of a coral reef. This skeleton can be hard or soft, but in the latter case, the corals grow faster. Coral reefs are filled with a myriad of coral species that form an ecosystem. They are home to a wide variety of animal species and serve as a refuge and food supply. Coral, like all animals, breathes oxygen and emits CO2. Except for the deep-sea coral, it is in symbiosis with a microalgae that lives inside its calcareous skeleton. The algae needs light to photosynthesize and transform CO2 into oxygen. All the waste products of the algae are assimilated by the coral, so they provide 80% of their needs. The remaining 20% is plankton that the coral captures with its small tentacles. The coral reefs contribute to enrich the marine fauna of the time. This particularly interesting period for the history of life will, however, be cut short by the first great crisis and mass extinction. The oceans on Earth teem with life, yet 6,000 light-years away a terrible cataclysm is brewing that will bring about the extinction of many species. In the Milky Way, a star at the end of its life explodes into a supernova. A gigantic explosion of gamma rays gushes out as powerful radiation. It is one of the most destructive phenomena that occurs in the universe. The energy released in about 10 seconds is equivalent to that which could be produced by 10 suns. The emitted rays disperse in the cosmos and head towards the Earth at the speed of light. They penetrate the solar system and pierce the asteroid belt. Once arrived at the level of the atmosphere, the destructive rays exterminate the air molecules and blow the atmosphere. The traces of the supernova shine in the sky alongside the sun. The impact of gamma rays has irreversible consequences for living organisms. They destroy 30% of the ozone layer, letting ultraviolet rays invade the surface of the planet. The light increases, becoming 10 times more powerful than in the Sahara. Plankton, the basis of the food chain, is destroyed, and hunger follows for the plankton eaters. Trilobites, which are used to incubate their eggs in surface waters, see their larvae die under the effect of ultraviolet rays. Many corals do not survive. The phenomenon extends over the entire surface of the planet. The base of the food chain being compromised, all species of animals are suffering from starvation. A few months later, a toxic atmosphere invades the planet, rich in nitrogen dioxide. A thick layer of haze obscures half of the sun's rays. There is less light and less heat. Temperatures drop to -12 degrees Celsius or 10 degrees Fahrenheit. The survival of many species is then threatened. The nautiloids laid their eggs, but the cold slows down the embryonic growth, and bacteria appear. Some of them see the day anyway, but the world that offers itself to them is chaotic. Food is far from abundant, and living conditions are hostile. They rely on the strength of their shells to shelter in the ocean depths from the effects of the Earth's cooling. As the temperature drops, mobile animals move around and try to find shelter. But corals, sponges, and other brachiopods cannot escape. Their calcium carbonate shells are difficult to form in cold water. They disappear. The generalized cooling of the planet causes an unpredictable climate due to important temperature differences. Strong ocean currents are formed, as well as violent disturbances. A hurricane blows on the Earth. Weakened animals are swept away without resistance. Some find refuge in the turbulent waters. The Orthoceras and its long shell do not resist the storm. The nautiloid can take refuge in the deeper waters while waiting for the lull. The storms follow one another. The corpses pile up on the shore. No predator is there to devour them. The few surviving species are undernourished. Over the years, the Earth continues to cool. A new ice age begins. The snow piles up, then becomes denser until it builds huge glaciers. These glaciers suck the water from the oceans, which saw their level decrease by several tens of meters. Astraspis proves to be very resistant in the chaos. It follows the retreating sea and acclimates to the cold water. It swallows everything and anything. This facility allows it to continue to feed, whereas others that only feed on a specific prey do not survive if this prey disappears. Thanks to the adaptability of the Astraspis, a new generation of fish is born. This time, the bones and muscles of the gill take on the function of absorbing food. Another animal clings to life, the Eurypterid. It too follows the retreat of the oceans. With the disappearance of the Orthoceras, it has moved up a rank in the food chain. Its smaller size allows it to eat less and to adapt to the food crisis. The decrease of the ocean level draws new landscapes. Reefs appear above the water level. As glaciers continue to evolve, icebergs are forming under the surface of the water, real threats to aquatic habitats. Corals are being violently destroyed. Large areas of marine habitat are now visible on the surface, but are being eroded by the weather. The resilient ones that survive must follow the ocean, even though the habitats are shrinking. The causes of the Ordovician glaciation are not yet certain. If some think that it would be due to the explosion of a supernova near the Earth, this is difficult to prove because the traces of the latter have long since disappeared. Other hypotheses submit the idea of a sudden fall of CO2 due to the explosion of plants on the surface of the Earth, leading to a global cooling. The only thing that is certain is that the Ordovician glaciation was responsible for the disappearance of many species. This event caused the extinction of 50% of genera and 85% of species. 500,000 years after the extinction began, the Earth warmed up and the glaciers began to melt. Survivors must adapt to this new upheaval. Species that are widely distributed across all continents are more likely to survive. The Orthocera, although in bad shape, is still around. It is weakened, smaller, and becomes a prey. The Eurypterid becomes a formidable predator. The roles are reversed. The Eurypterid adopts new behaviors. The accelerated drop in sea level has led to the development of lungs in some species. The Eurypterid can now drag the carcass of its prey on the shore. Another evolution is visible in fish, the appearance of jaws. The acanthodians, scavengers cousins of the Astraspis, are no longer content to wait for the remains to come to them. They tear the flesh right off the carcass. It takes 3 million years for the Earth to calm down. The toll is heavy, but thanks to nature's astonishing form of resistance, life resumes its course. Temperatures rise again. The melting of the glaciers fills the oceans again. This rapid rise is due to the melting of water stored on the continents with a low oxygen content. The ocean is depleted, and the effects are harmful to the biosphere. At the same time, vast marine habitats are being rebuilt that welcome some known species, but also new ones. Acanthodians and Astraspis swim together and begin to venture into lakes and the emergence of the first plants from the waters builds, a few million years later, an ideal habitat that encourages the first animals to venture out and finally settle there. These first adventurers are segmented creatures, the ancestors of our millipedes. Because of their chitin covering, they have facilities to move on the ground. At first, they do not stray far from the water's edge, but then they discover that mosses contain moisture and food through plant debris and spores. Although these myriapods are not really millipedes, some of them could reach considerable sizes, up to 2 meters long. Being basically adapted to aquatic life, they had to evolve. They acquire an external skeleton and develop a different way of breathing. Myriapods are equipped with a system of breathing tubes called tracheae. Each tube leads to the side of the carapace and splits into an increasingly fine network that leads to the organs and tissues, even penetrating each cell in order to bring them oxygen. The mode of reproduction of terrestrial life also required some changes. The spermatozoa can no longer move in the absence of water. The male and female then go to meet each other in order to transmit their sex cells. A rather laborious process, but one that bears fruit. These undulating, frisky creatures are prime prey for other species. The animals are gradually becoming more and more resistant to humidity and are continuing their terrestrial adaptation. At the same time, the plants also evolve. The Lapitous Ocean closes between the continents Laurentia, Baltica, and Avalonia, which join together and now form Laurasia. Gondwana is still located in the high latitudes, but the ice cap is less extensive. The climate stabilizes, but it is much warmer than today, with a high concentration of CO2 in the atmosphere. The first plants are simple organisms. They need CO2, light, and water. From 420 million years before our era, plants diversify and develop new functions, allowing the circulation of water and nutrients. This is a decisive period for the sustainable establishment of land plants. Mosses and other primitive species do not have roots. Their vertical stems are born from horizontal stems of the same nature, the stolones, which spread on the surface of the ground. The stolones capture water. However, in some of the drier parts of the world, plants need roots to draw the water they need from the depths. 3 kinds of plants with buried structures appeared 420 million years ago: lycopods, horsetails, and ferns. Each of these new plants has stems inside, which solid vessels allow the water absorbed by the roots to circulate. They acquire rigidity that allows them to reach significant heights. Green plants depend on sunlight for the synthesis of the substances they need. This evolution of size is then a considerable asset. The smallest plants can remain in the shade and risk dying if they are deprived of light. Lycopods, horsetails, and ferns take advantage of their new vigor to grow and become trees. Lycopods and horsetails are found in swamps and reach heights of up to 30 meters or 100 feet. Some trunks measure 2 meters or 6 feet in diameter. The landscape of the land is changing, with forests being abundant and evergreen. Some species move inland from the swamps to the ferns. The latter have large leaves spread out on the ground in order to capture as much light as possible. The animals are confronted with a change in the configuration of the forests, and this puts at risk certain species which had before access to a large variety of leaves and spores on the ground. Their food sources are now elevated towards the sky. The trunks block out a large part of the light, and the forest floor is depleted of vegetation. Some spaces even remain completely bare. This is how some polypod animals start to climb trees. Cooksonia are the first known plants with vascularized tissues. These plants are small not exceeding 8 centimeters or 3 inches. They have a stem without leaves, flowers, or roots. Each branch ends in a sporangium, a rounded structure that contains spores. The cocconia are attached to the ground with thin ridges. The warm climate is also conducive to the appearance of Rhiniopsida, a vascular plant. It presents axes with ramifications and does not have roots but filaments. It sinks in the substrate, and its aerial axis rise and divide each time in 2 identical axes. Its conductive vessels are grouped in the center and covered with a bark, then with an epidermis with a cuticle and stomata. The aerial axes contain the sporangia filled with spores. 20 million years later, when the Lapitous Ocean closed, a mountain range was built within Laurasia. Under the effect of erosion, the chain is destroyed. The hot and humid climate dissolved the limestone. The rock minerals degraded and turned into clay. Other minerals release iron during their degradation. The iron oxidizes, becomes insoluble, and settles to the bottom of the sea. With time, the sediments harden and form sandstone. They cover gigantic surfaces. It is the continent of the Old Red Sandstone. With the melting of the glaciers, the ocean level rises again. This is a period of great evolution for fish. Jawless fish spread, as well as the first freshwater fish. The aquatic life resumes its course, and the ocean is repopulated. The Sarcopterygians, a group of fish, appear, with, among other, the Panderichthys. This fish has a transitional anatomical structure, with that of the tetrapods. Its internal skeleton, made up of fins, reminds of Chiridian members. It measures approximately 1 meter or 3 feet, and its head is similar to that of our current catfish. It has primitive lungs. Graptolites also roam the seas in colonies. These animals resemble coral polyps made of coiled and serrated tubes. These animals are grouped around a stem. They can measure from 2 millimeters to 1 meter or 3 feet in length. Some live on the surface of the ocean and drift with the currents. Others attach themselves to algae on the seafloor. A new fish appeared 375 million years ago, a link in the chain between fish and tetrapods, the Tiktaalik. This bony fish looks like a being that would be a curious mixture between fish and alligator. It has scales and fins with rays like all bony fish, but its rather massive pectoral fins resemble the limbs of the first tetrapods. They are made up of an articulated and rather rigid bony skeleton, which allows the animal to move its body in the lagoons. Its wrists and fingers allow it to support its weight and to move on the ground. Its pectoral fins are covered with large muscles and can flex like a wrist joint. This characteristic allows the Tiktaalik to stop at the bottom of the water and to face the strong currents. It has a powerful rib cage to support its body out of the water. The Tiktaalik ventures on land to hunt for new prey. It has gills, but also primitive lungs. The latter were initially developed not for life out of water, but to adapt to shallow and warm aquatic environments, whose waters are depleted in oxygen. Fish, which today are one of the most primitive forms of life, are then one of the most modern. In some cases, they even take on the appearance of real marine monsters. Placoderms roam the seas. The placoderm is a megapredator that dominates the seafloor from the top of its 8 meters or 26 feet length. It is muscular and armed with a sharp jaw, allowing it to have a varied diet composed of algae, mollusks, and other fish, Its head and thorax are covered with thick bony plates that protect its vital organs during attacks. Its two jaws are completely toothless and covered with sharp-edged bones. It is thus able to cut its prey in two. Facing the placoderm, the gigantic Dunkleosteus reaches up to 10 meters or 32 feet in length and 5 tons. This ferocious animal is an outstanding predator. Its jaw, although devoid of teeth, is nevertheless sharp like no other. It crushes its prey and then spits out the parts that are indigestible. Its head is protected by bony plates. The Eusthenopteron is an agile predator which has the particularity to have fins conceived like human members. Its endoskeleton comprises, in the anterior fins, a humerus, an ulna, and a radius distinct, and in the pelvic fin a femur, a tibia, and a fibula. 372 million years ago, the Earth is calm. It is good to live. A warm and humid climate prevails, vegetation abounds, and life proliferates and evolves. Large ferns and trees shape the landscape. Tiny insects inhabit these primitive forests. In the ocean, life in many different forms swarms. The coral reefs extend, and the seabed is a veritable underwater city in which inhabitants have found refuge. Sponges, trilobites, corals, insects, nautiloids remain. Fish are then one of the most advanced species. In parallel to this explosion of biodiversity, a cataclysm is preparing, deep in the bowels of the Earth. For even if the planet's surface remains calm, its heart is boiling. A gigantic plume pierces the ocean floor. Very hot gases are expelled from the center of the Earth, and jets of hot water surge with unprecedented force. Underwater landslides occur and destroy the reefs. For millions of animals, it is impossible to survive. Fish succumb to the heat. Volcanic eruptions and lava flows stimulate the activity of the tectonic plates. The ocean floor cracks. A new oceanic crust and new underwater volcanoes are formed. The plume infects the ocean. When the molten lava comes into contact with the seawater, it releases toxic substances. The contamination first affects the new generations. The eggs of the Eusthenopterons do not survive in these poisoned waters. Over the years, the released gas, mostly carbon dioxide, invades the Earth's atmosphere. The latter is gradually loaded with greenhouse gases. As a result, the temperature at the Earth's surface increases. The heat of the oceans is no longer redistributed. Previously, the polar cold tried to warm up towards the tropics, and vice versa for the cooling of tropical waters. From now on, the ocean freezes, the currents stop. The water in the oceans is getting warmer. The reefs can't stand it, and neither can the Tiktaalik. His habitat evaporates, but he makes a decision that will allow him to save his skin. He gains the dry land in order to move away from these deadly waters. It is thanks to its anatomy that it can afford this change of habitat. Its respiratory system, half gill, half lungs, makes its life on ground and in the seas possible. It has articulated wrists and a mobile neck, and can move by crawling, or at least by wriggling. At this time, the Earth is less hostile than the sea, and the Tiktaalik discovers a new environment and new sources of food. They fared better than most other fish, who once all the water in their environment had evaporated, found themselves trapped and condemned under the hot sun. 250,000 years after the eruption, the giant plume persists. The Earth is subjected to a high level of carbon dioxide and a sharp rise in temperature. It becomes an ideal ground for the proliferation of plants. It is a real paradise for plants that grow excessively and invade the land. Over the years, the dead leaves fall on the ground and accumulate in mass. They rot and form the first layer of humus. This humus, rich in nutrients, is then carried to the oceans by the rains. The algae feed on it and develop immoderately. To do so, they use oxygen and asphyxiate the aquatic life. The seas become saturated with plants, and the abundant kingdom of animals that remained is dying. A million years ago, eruptions began to hit the Earth. Until then, they had been occurring at sea. But now a gigantic volcano is gathering its forces to erupt, this time on land. The Earth shakes. The air is filled with sulfur. Geysers of lava are spat out by the volcano, several hundred meters high. A cloud of ash forms in the sky, bringing the planet into a terrifying darkness. A black veil hides the light of the sun, and the mixture of the gases gives the sky an orange color. Most of the ash dissipates into the atmosphere, but the gases that penetrate the stratosphere can remain there for several years. These gases act as a barrier to the sun's rays and plunge the Earth into a volcanic winter. Temperatures drop sharply. The ocean goes from 32 to 21 degrees Celsius. That is to say, from 90 degrees Fahrenheit to 70 degrees Fahrenheit. The Tectonics, who had found refuge on dry land, find themselves confronted with an unknown but invincible enemy: snow. It is cold. Their population will not survive it. As with the last mass extinction, a wide variety of causes, sometimes concurrent and often interdependent, have been proposed to explain the Devonian extinction. In any case, the volcanic winter is ending. The Earth is devastated. The marine fauna is globally affected by this mass extinction. 21% of the families, 50% of the genera, and about 75% of the marine species have disappeared. There are still some building groups in the reef environment that survive as isolated individuals. Brachiopods, cephalopods, and trilobites are experiencing a high rate of extinction. The evolutionary dynamics of the arthropods is nevertheless not curbed. Bacteria and algae fill the void left by the animals that are becoming rare. The environment is similar to that of the Precambrian. The trees which had led to its loss will now contribute to give life to the Earth. They produce more and more oxygen, and slowly the temperatures will increase until they stabilize. The seasons reappear, and life can once again diversify. Panderichthys began a transition to legged evolution a few million years ago. They have curious fins. Fish fins are normally made of spiny rays, which are either rigid or soft and flexible. In both cases, they are exoskeletal pieces that support the non-muscular skin fold of the fin. In Panderichthys, the fins are articulated on only one element, without any other ray. They leave a glimpse of humerus, a radius, and an ulna, then end with a flexible veil covered with scales. It is this famous veil that today gives way to a new structure, the fingers. These fingers would be an abnormal embryonic development of the end of the fins. Usually, the end of the fish embryos forms an apical ridge, which generates the growth of the bony rays of the fin. Once all the rays are formed, the ridge peels off, which stops the formation of new bony structures on the fin and ends in a veil. In the first tetrapods, this famous ridge did not come off, and the bone structure continued on its way, giving shape to the arm, forearm, wrist, and then the phalanges. This is how new forms of aquatic animals appeared: tetrapods equipped with functional gills, covered with scales, feeding on fish, and endowed with limbs with fingers. Initially, this evolution is certainly not an adaptation to terrestrial life, but rather to the muddy environment and cluttered with branches and roots of trees. These very rudimentary legs are similar to a kind of paddle. They are rigid, not very functional, and are not at all adapted to support massive fish. A few million years later, the sea level continues to drop, and the land surface becomes larger and larger. Bodies of water become isolated from each other. Tetrapods are better equipped to live in this new environment. Now equipped with gills and lungs, they are able to move from one water body to another. The Ichthyostega is one of the first vertebrates to have 4 legs. It is a descendant of the long-extinct Tiktaalik. The Ichthyostega lives near rivers, lakes, and marshes. It is forced to go on land to look for food, which explains why its future generations will be more terrestrial than aquatic. Thanks to its long pointed teeth, it feeds on fish, insects, but also small terrestrial animals. It can reach up to 2 meters or 6 feet in length, and 20 centimeters or 8 inches in height. Its skull resembles that of primitive fish, with small eyes located on its dorsal side, which gives it a very good field of vision. Its body is covered with scales, and it has a very strong spine, due to the adaptation to terrestrial life. Although it has some kind of legs, it is rather at ease in the aquatic environment, since its 7 fingers are connected by a membrane. But it is an easy prey for other predators with which it must compete for food, which explains its big step for the dry land. Alongside Ichthyostega, Acanthostega evolves between terrestrial and aquatic environment. With a length of 60 centimeters or 23 inches, it has 8 fingers on each hand. Its stiff-jointed limbs prevent it from bending properly and do not allow it to lift its weight on land. They are more efficient for swimming. It will need further development to be completely comfortable out of the water. It breathes thanks to its lungs and reproduces in water. It has a lateral line that allows it to detect vibrations. 360 million years ago, the Earth is enjoying a relative lull. The average temperature on its surface is 20 degrees Celsius, or 68 degrees Fahrenheit. It is warm and humid in the lower latitudes, although the southern part of Gondwana is covered with ice. Forests and swamps abound, and lush vegetation flourishes. As the plant matter decays, it turns into the black or dark brown sedimentary rock, known as coal. This rapid expansion of plants leads the Earth into an oxygen age. As all plants photosynthesize, the concentration of oxygen in the air increases until it exceeds the current concentration. This hyperoxygenated atmosphere favors the development of arthropods, and even some vertebrates, until they reach disproportionate sizes. The anatomy of arthropods explains this gigantism. Their open circulatory system allows their blood to circulate freely in the body cavities, bathing the organs, and not inside vessels. Their body is covered with small openings, the spiracles, which allow oxygen to reach the circulatory system. Oxygen then diffuses into the tissues through small tubes, the tracheoles. Variations in the concentration of atmospheric oxygen will thus have an impact on the size of arthropods. The Earth's tectonic plates continue their movements. Laurasia, which includes Laurentia, Baltica, and Avalonia, collides with Gondwana, which includes all the other land masses. Middle Europe emerges as high mountains. The Appalachians slowly rise in North America. A new supercontinent, Pangea, begins to form. The latter includes almost all the existing continents, except Siberia for a while. A new generation of plants appears, whose sexual generation lives at the top and no longer at ground level. Among them, the cycads. Dressed with large rough fronds, cycads look like ferns. Some plants produce spores spread by the wind. Others produce larger ones, which remain fixed to the mother plant. They evolve in conical phallus, in which ovules are differentiated. When a spore is carried by the wind in the phallus, it germinates and forms a long tube, which digs its way in the female cone. Once completed, a sperm is produced, looking like a majestic sphere that can be seen with the naked eye. It slides down the tube, fuses with the egg, and fertilization takes place. In this time, other plants appear. The conifers with pines, cedars, larches, and firs. The conifers protect their trunks from external attacks by secreting resin. It is fluid and flows from a notch. It is composed of turpentine, and once the turpentine has evaporated, it freezes. The resin then takes on the appearance of a gum, which closes the wound and traps the insects that touch it. The appearance of the amniotic egg is a real revolution in the evolution of species. This egg is that of birds, reptiles, and monotremes. The shell of the amniotic egg is hard and porous. The embryo inside can breathe oxygen from the air, but not from the water. Thus, if an amniotic egg is immersed in water, the embryo dies of asphyxiation. The yolk of the egg is a food reserve sac, intended to feed the embryo, which allows it to hatch at an advanced stage of development. Inside the egg, the embryo evolves in a sac filled with amniotic fluid, called amnion. It is protected from dying out and shocks. Amniote species are totally free of the aquatic environment. At the same time, amniotes develop a dry and relatively waterproof skin, which slows down the water losses. Henceforth, they can move away from the water points and venture towards zones inaccessible until then. Insect wings begin upstream as dorsal blades. They then acquire a circulation. There are 6 of them at this time. Wings confer a significant evolutionary advantage in the world of living things. By mastering the air, these insects become dominators of the land. By flying, the insects move at a crazy speed. They multiply and are the first to reach virgin land, the other side of the river, or the tops of trees. They escape from their numerous predators on the ground, such as spiders, amphibians, or scorpions. but the threat is now coming from among them. The oldest winged insects and the largest airborne predators of this era are the dragonflies. There are many species of them. At that time, dragonflies, like the Meganeura, took advantage of the lack of competition to grow to gigantic sizes, up to 70 centimeters or 28 inches wingspan. But as soon as the air starts to become populated, the giant dragonflies disappear. Dragonflies have 2 pairs of wings articulated with their body. This allows them to move vertically and travel through the air at speeds of over 30 kilometers per hour, or 19 miles per hour. To avoid collisions at such high speeds, they are equipped with sharp senses. Their 2 huge faceted eyes give them a vision of almost 360 degrees and an amazing precision. Dragonflies are daytime shoehorners. Hardly more discreet, the Paleodictyopteron roams the air with its 55 centimeter or 22 inch wingspan. These insects are characterized by mouthparts under the head that allow them to suck sap. A little further down on the ground, the Pulmonoscorpius is a kind of large scorpion that reaches several tens of centimeters. It feeds on other arthropods. Arthropleura likes the abundant vegetation of this time, and it does not pass unnoticed. The genus of millipedes is one of the largest terrestrial vertebrates that ever existed. It measures up to 2.5 meters or 8 feet long and weighs about 50 kilos, that is to say 100 pounds. Its large size repels predators without counting its carapace, which serves as protection. It is herbivorous and thrives in wet and swampy environments. In spite of its cumbersome size, it moves easily on the ground of the forests. It happens to find itself in front of Diplocaulus, an amphibian which marks the spirits because of its original anatomy. Indeed, its particularity is its spectacular boomerang-shaped head, much larger than the rest of its body, which gives it a disproportionate look. It measures about 1 meter in length and some 10 centimeters or 4 inches in height, and weighs about 7 kilograms or 15 pounds. It lives between ponds and marshes and can go back and forth between the aquatic environment and the land. It eats fish and small insects. During its search for food, it tries not to cross paths with pelycosaurs for whom it would be an easy prey. Among the best known of this genus, the Dimetrodon is noticed by the large sail it carries on its back. This giant lizard can reach up to 4.5 meters or 15 feet and weigh more than 250 kilograms or more than 550 pounds. It is one of the largest predators of its time. Its sail is made of elongated spines starting from the vertebrae. Its numerous and large teeth allow it to attack many animals: fish, tetrapods, reptiles, amphibians. The presence of insects strongly contributes to the revolution of the plant world that is beginning. The first trees existed in 2 successive forms, sexual and asexual. Thanks to their high size, spores are carried and disseminated easily by the wind. For the sexual cells, the meeting is ensured in the water by the male cells, imposing them to maintain themselves close to the ground. For ferns, horsetails, and lycopods, this mode of reproduction is not a problem. The spores develop into small shoots, the thallus. Once fertilized, they evolve into small plants that will carry the spores. But the thallus on the ground is vulnerable. It attracts animals and dies if it is dried out. In addition to the wind, Flying insects help to disperse the spores by moving from tree to tree. The continental block Siberia joins the already welded block of Laurasia and Gondwana. Pangea is now complete. This last collision raises the Ural, a mountain range. The superocean Panthalassa, ancestor of the Pacific Ocean, surrounds Pangea. It takes a C shape with the equator for center and is barred by the Hercynian chain. The ocean that forms in the hollow of the crescent is the Tethys Ocean. The formation of such a supercontinent has repercussions on life. On the continent, the distance of the lands of the center of Pangea compared to the ocean causes a strong decrease in precipitation. Huge deserts are formed in these regions. The aquatic environment is also modified because the length of the coasts having decreased, the surface of the coastal waters also, and consequently, many marine species disappear. Pangea remains a cradle of life, lined with forests, fresh springs, and creatures stranger than the others that are found everywhere. Reptiles adapt to these conditions and develop thermoregulation systems. The therapsids, or mammalian reptiles, take on a new form of protection: fur. This new appearance of reptiles is reminiscent of our current mammals. Therapsids are the prey of an outstanding predator, the terrible Gorgonopsian. This carnivore has overdeveloped canines and incisors, which allows it to attack both small and large animals. It can reach the size of 5 meters or 16 feet long and weigh up to 350 kilograms or more than 750 pounds. Despite the apparent calm and equilibrium that thrives, the bowels of the earth are still boiling. Just over 250 million years ago, in present-day Siberia, a large province called the Siberian Traps was formed. It is under the Earth's crust that everything is played. Gigantic columns of magma are heading towards the surface. Subjected to a strong pressure, the ground spreads out. Cracks appear over several hundred kilometers and miles, as if the Earth was opening in two. Streams of lava flow out of it. Volcanoes eject astronomical quantities of molten rock. In no time, the region is like a huge inferno. The tremors resound on all the surrounding lands. The animals present in the vicinity are immediately burned. The lava flows spread very quickly, and this is only the beginning. The eruption of the Siberian Traps does not stop. That is what distinguishes it from the usual eruptions. It pours its flow of lava for 1 million years. The Earth being at that time formed of a single continent, the ocean of liquid rock spreads everywhere. After about 10 years, the volcanic gases accumulate in the atmosphere. Gigatons of carbon dioxide and sulfur are volatilized, with dramatic consequences for the climate. The carbon dioxide captures heat, and the sulfur obstructs the passage of sunlight. Episodes of cooling and warming follow one another, making life very difficult. Oxygen levels in the air drop, and animals struggle to breathe. Some of them show amazing resilience. Smaller animals are more successful in finding refuge, and those living in communities combine their strength to survive the nightmare. Cold-blooded animals are more resistant to climate change because they can regulate their body temperature. They need less energy to survive. When the basaltic rock bursts out, it transforms, in contact with the air, into solid rock of a deep black. Immense mountains are formed, drawing a landscape of desolation. the living is killed or pushed away. And yet, the Earth is not at the end of its sorrows. Volcanic sulfur dioxide mixes with water vapor to form sulfuric acid. Torrents of acid rain are now falling on the planet. The trees are ravaged, and the vegetation is decimated. Shelter is now scarce for the survivors. The warming phases of the planet cause a cascade effect of warming of the oceans. The aquatic environment suffers from a lack of oxygen and threatens the marine species. The methane hydrates present at the bottom of the oceans are maintained in a solid state thanks to the pressure and low temperatures. Under the effect of global warming, these methane hydrates are in their gaseous state and methane is released. This greenhouse gas is 21 times more powerful than carbon dioxide. Vegetation, which usually regulates the proportion of greenhouse gases in the atmosphere, is absent. The warming accelerates considerably. The flora is dying out, suffocated under this immeasurable heat. The base of the food chain is threatened, and famine sets in. The herbivores are the first to be threatened, followed by the species that fed on these same herbivores. In all Pangea, the vegetation disappeared. Life is close to total extinction. Heavy rains carry the dead plants to the ocean. The ocean fills with waste that rots because of the heat. Air and water no longer circulate. The majority of the ecosystems that predominate in the aquatic environment are threatened. Bacteria subsist in this gigantic landfill and produce hydrogen sulfide, a toxic gas when released in large doses into the atmosphere. It is carried all over the surface of the planet by the winds and causes the death of a great number of animals. The Earth has entered a vicious cycle that is killing slowly. 150,000 years after the Siberian Traps eruption began, the lava flow reaches a depth of 1,600 meters, or more than 5,200 feet deep. The lucky few who survive adapt, and new generations appear. It is not until 500,000 years after the eruption began that it began to subside. The traps poured more than 6 million square kilometers of lava over the entire surface of the Earth, representing an area equivalent to 2/3 of the United States. The Permian extinction is the most important that the living world has endured. It is 70% of the species that disappeared on the continents. In the oceans, this extinction affects half of the families, 3/4 of the genera, for a total of 95% of the species. Trilobites, reef-building corals, and among others, pedunculated echinoderms are disappearing forever. The tropical paradise has been replaced by a hostile world, and it will take a very long time for the Earth to recover from this catastrophe. Under the effect of plate tectonics, Pangea begins to fracture gently. It is only 50 million years later that rifts begin to separate North America and Africa. Following the formation of this rift, the Atlantic Ocean opens and divides Pangea into two parts, a northern part and a southern part, that will be Gondwanaland and Laurasia. The passage of the ocean near the parts that were previously the center of Pangea humidifies this environment that remained dry and arid until then. From now on, several continental masses are in place, and the oceanic currents are favored. Interactions between terrestrial and aquatic environments increase, and new ecological niches appear. Species are diversifying. Climate change also plays a significant role, in the diversification of plants. Shortly after the terrible mass extinction that the Earth suffered, the huge continental plate that covers it, Pangea, broke up. The Panthalassa Ocean has been sinking into the western part of Pangea for a few tens of millions of years. This oceanic opening widens, advances towards the west, and a new ocean is formed, the Tethys Ocean. Pangea is divided into two continental blocks. In the north, Laurasia, and in the south, Gondwana. The development of the Tethys Ocean has consequences on the climate, on the ecology, and on the geography of the Earth. The climate, which was predominantly continental, becomes oceanic. The rise in sea level is caused by the activation of new oceanic ripples. Biodiversity flourishes thanks to the flooding of new continental surfaces. Separated lands, however, limit exchanges between individuals. Eventually, some populations will be completely isolated and will become full species that will evolve and diversify on each continent. For now, the planet is empty in terms of biodiversity. The Great Permian Extinction left only a few survivors. Faced with these vast expanses to conquer, they have the opportunity to evolve and diversify. This is the beginning of a new adventure in the history of the Earth. The Tethys Ocean, its heat and its dizzying depths are a godsend for the marine fauna. It is hot on Earth. The level of oxygen in the atmosphere is low, the level of CO2 is high, and the atmosphere on the planet is like a huge greenhouse. The flora has suffered the catastrophe of the Siberian traps, but it was much less brutal than for the animal world. Even if vast areas were devastated, in only a few thousand years, a flourishing vegetation decorates again the continental surface. The animals that survived conquered this new environment and settled there. Time passes, they will adapt, evolve, and new species will appear, creating new branches. This is evolution. Insects, on the other hand, continue to evolve, improving over the years. They are everywhere, already present by millions. Jawed butterflies, pollen crushers, flies already very similar to our current flies, or the first cicadas, and the first bugs share the air. "250 million years ago, the seas were repopulated by a multitude of new inhabitants. Among them, mollusks flourish fully, including belemnites and ammonites. The latter are present in greater numbers. Ammonites flourish and proliferate in waters that are 250 million years old. They are related to the class of cephalopods, which literally means feet in the head. Their feet are a kind of tentacles that surround their head. Several species of ammonites have been identified. They live rolled up in a spiral shell that is divided into chambers. Most of them are filled with gas or water to guarantee the buoyancy of the animal. To go down to the seabed, ammonites fill their lodges with water, and to go up to the surface they fill them with gas. The animal occupies the last compartment. Throughout their life, ammonites grow and build new lodges. These mollusks populate all the seas of the world, rather in the open waters than in the seabed. They present a great variety of size. Even if most of them measure a few centimeters or inches, some can reach up to 2 meters or 6 feet in diameter, the size of a tractor wheel. They are good swimmers. Alongside ammonites, belemnites have a very different shape, rather elongated, reminiscent of a javelin. Their head is provided with a beak and 2 prominent eyes. Their 10 tentacles have hooks and suction cups that allow them to catch their prey. Some species have a pocket of ink that they release to conceal their escape from predators. "15 million years later, small groups of Archosaurian reptiles took over the ecological niches left vacant after the previous mass extinction. In the seas, hybodonts are found in large numbers. These fish were initially small, between 20 and 30 centimeters, or about 10 inches, and fed on tiny prey. A few million years later, they grew to a size of 3 meters or 10 feet in length. Thanks to their great capacity to adapt to salt water, they diversified. They developed teeth, allowing them to tear and crush. The class of condycthrians, distant cousins of today's sharks, are at the top of the food chain. But in front of them, new marine inhabitants are trying to make a place for themselves underwater: the reptiles. Some families are more like aborted evolutionary attempts, like placodonts. These marine reptiles feed on hard prey, shellfish or crustaceans. At the beginning of their appearance, they resemble iguanas, only bigger, since they reach 1 to 2 meters in length. In order to protect their bodies, placodonts develop bony plates on their backs that resemble a carapace. At the end of their evolution, they look more like our current sea turtles. Their size allowed them to ward off the first predators, but over the years, new reptiles, larger and more ferocious, appeared, causing the disappearance of placodonts. Other reptiles, on the other hand, had a long and grandiose reign, such as the ichthyosaurs. These animals frequent the seas of the blue planet. The oldest ichthyosaurs resemble finned lizards, while the most recent ones resemble tuna, but their characteristics remain unique. Their leg bones have evolved into swimming paddles and are reminiscent of a corncob. Their vertebrae resemble an ice hockey puck, and their eyes are encircled by a bone called a sclera ring. When ichthyosaurs dive and swim, the water exerts pressure that can distort sensitive parts such as the eyes, so the sclerotic ring strengthens the eye and gives the animals highly developed eyesight for their size. Ichthyosaurs measure from 70 centimeters or 30 inches to 20 meters or 65 feet in length. They are fond of belemnites, fish, and other marine organisms. Like all living things, they need to breathe. Although their oxygen consumption is low, they have lungs and must regularly come to the surface of the water to breathe. Ichthyosaurs are viviparous. Their eggs are not laid, but incubate in the genital tract of the female until they hatch and release their young in the open sea. The latter have subsequently acquired the ability to regulate their temperature. Ichthyosaurs move by swimming in a particular way. They undulate their whole body like lizards, and can thus accelerate easily to hunt or flee. Their more recent representatives, which are more like tuna, only undulate the posterior part of their body. This evolution in their way of swimming generates an important modification of their living environment. If, at the beginning, they were confined to the continental shelf, from now on, they ply the great waters of the oceans. It is, moreover, a generalized evolution. The fragmentation of the pangea generates the dispersion of the marine fauna, which colonizes the high sea. On Earth, the surviving families of the previous extinction are the most widespread. At the top of the food chain, archosauromorph reptiles dominate. The more basal ones give rise to the archosaurs, and then emerge the pterosaurs. Pterosaurs are insect-eating flying reptiles, of which there are 150 species. For a long time populated only by insects, the air environment welcomes vertebrate animals. The Quetzalcoatlus is one of the largest specimens that can reach 12 meters or 40 feet wingspan, the equivalent of a small passenger plane. It has an elongated head, a long neck, and its tail is almost non-existent. The wing of the pterosaur is formed by a membrane of skin, connected to the hind limb, and supported by the fourth finger very elongated. In order to remain light during their numerous flights, pterosaurs have hollow bones. These animals fly over the forests of ginkgo and ferns in search of food. Since they do not have a highly developed olfactory center, they use their vision to flush out insects, fish, and birds. Although they are comfortable in the air, pterosaurs also frequent the aquatic environment and move around on land. Their feet are webbed, and they adopt a quadrupedal gait to move. On land, the Archosaurian lineage produced the first crocodiliforms with Protosuchus. This animal has an appearance very similar to that of crocodiles, with a large mouth decorated with powerful teeth and a long tail. The lineage of archosaurs gave birth to the first dinosaurs a little later. This is still a far cry from the giant predators we imagine when we think of dinosaurs. The Euraptor is one of the first known dinosaurs to have appeared on Earth. It later gave birth to the long-necked sauropods. It is about 1 meter or 3 feet long and 40 centimeters or 16 inches high, the equivalent of a large dog. It has been called the Dawn Hunter. It is the fastest animal of its time. It is omnivorous and feeds on other reptiles, insects, but also on all sorts of other foods that provide it with proteins and vitamins. The Chloroplasts is a bit bigger than the Euraptor. It can reach up to 3 meters or 10 feet long and 55 centimeters or 20 inches high. Its large tail occupies half of its body. Thanks to its narrow mouth, it catches small prey quickly. When hunting in a pack, like our modern wolves, it attacks larger prey. These different species shared the land with the first herbivorous dinosaurs, which were larger and more numerous. Among them, the flatfish is an animal that measures up to 10 meters or 30 feet in length and can weigh up to 4 tons. Its diet is mainly composed of plants. Thanks to its very sharp and robust teeth, it crushes the plants that it extracts directly from the tree. Its long neck, composed of 10 vertebral elements, gives it strength and power to defend itself and allows it to pull plants even from the treetops. Next to the first dinosaurs, the mammalian reptiles are largely represented by the order Therapsids, but their population tends to decrease due to the emergence of new branches during this period. This does not prevent the Lystrosaurus and the huge Lysowisia from roaming the wilderness. The Lystrosaurus is a mixture of mammal and reptile. It measures 1 meter long and 1.5 meters high. Its fangs protrude from its upper jaw, which gives it a fearsome look. It has a beak that resembles that of turtles, ideal for chewing plants and satisfying its needs as a large herbivore. It sometimes crosses the path of the Lysowisia, an enormous animal which reaches the size of our current elephants. This herbivore uses its long beak to catch and crush vegetation. The Lysowisia is the prey of carnivorous archosaurs and is regularly hunted by them. The first mammalia forms appear a few million years later. They are the intermediaries between cynodonts and mammals. Under the appearance of our modern shrews, the Megazostrodon goes out at night to feed on insects and lizards. It is the prey of the first dinosaurs and must therefore be careful. Its small size, about 10 centimeters or a few inches, allows it to easily take cover. Adelabasileus is the oldest known ancestor of proto-mammals. It has in its ear a cochlea with a place close to that of the modern mammals. It is the link between the therapsids and the mammals that will soon appear. All these small animals live alongside formidable carnivorous predators. This is why most of them have adapted to life at night. In its skull, its cortex is more developed than that of the reptiles of the time, and it has a neocortex which ensures the cognitive functions. These attributes require a higher energy consumption. They must feed on energetic foods such as herbs, fruits, and insects. Two large groups of dinosaurs dominate and are differentiated by the anatomy of their pelvis. They are named Ornithischians and Saurischians. Saurischians have a pubis directed forward. They are, for the most part, carnivores, but we also find in this group the huge sauropods herbivores with long necks. The Ornithischians, as for them, have a pubis directed towards the back, what evokes the basins of the current birds. They are all herbivores. Mammals seem to have been forgotten during this long period when dinosaurs predominated. And yet, our distant mammalian ancestors, tiny and fearful creatures, lurked in the shadow of the giants. These primitive mammals have reason to be afraid. Dinosaurs diversified, expanded, and pushed the anatomical limits of life on Earth. They occupy most of the ecological niches, and what is left to mammals is small, dark, like caves, caverns, hollows in trees, or underground life. Surviving in such environments imposes constraints on size and lifestyle, but also an overdevelopment of the senses. Smell, sight, and hearing allow them to have a nocturnal life, which is less dangerous towards predators who are less active there. The organs of the senses being concentrated in the head, this induces a larger brain size compared to that of reptiles. And this is not all. The brain-burning energy that must be constantly renewed, specific adaptations appear. Mammals have warm blood and a coat that isolates them. The constant need for energy requires protein-rich food, such as insects or other invertebrates and plant seeds. These foods must be quickly digested to release energy as quickly as possible. This is how sharp teeth appear. Thanks to their dagger-sharp, powerful and sharp teeth, mammals now catch and kill insects, crush hard shells. These teeth are operated by strong jaw muscles. The means of reproduction evolves. While the eggs of reptiles and birds have already seen considerable progress with the appearance of the protective shell, this system remains limited, since the egg must be large enough to allow the newly born animal to be sufficiently developed to fend for itself. In addition, eggs and newborns attract predators. Mammals take a different approach. They keep and feed the embryo in the mother's body to ensure a better start in life. Although this method limits the number of offspring and depletes the mother's resources, it has enough advantages to become the primary mode of reproduction. The forces that had enabled the formation of Pangea a few million years ago are working hard to break it up. The first signs of the opening of the Atlantic Ocean are felt. The Earth's crust floats on the mantle, which is made of molten rock. The continental plates move, which causes an active circulation of magma. The more Pangea breaks up, the more volcanic activity intensifies, until exceptional quantities of lava gush out on the surface of the Earth. A new mass extinction begins. Monstrous jets of burning steam come out of the bowels of the Earth. The entrained debris rises to more than 1,500 meters or 5,000 feet above the ground. A fiery cloud surrounds the fauna and flora. Animals try to find refuge in the heights or in the water. But the fragmentation of Pangea has only just begun, and the consequences will intensify. On the edges of the future Atlantic Ocean, volcanic activity is intense. In time, it will form an immense magma province that will cover 11 million square kilometers, more than the size of the United States. Millions of animals succumbed. The Megazostrodon nests with its young in a burrow. Its small size allows it to take shelter and survive the hecatomb that will follow. It is now lava that flows from the heart of the Earth. Through all the cracks that have formed, flows of magma escape. The cracks can reach several tens of kilometers or miles in length. It is therefore an ocean of flames that flows on the surface of the Earth. Everything in its path at that moment is decimated, annihilated. The lava continues to gush out for months, for decades. The eruptions that cover the Earth with a layer of lava now have a toxic effect on the atmosphere. The gas dissolved in the magma rises to the surface, lowers the pressure, and diffuses into the Earth's atmosphere. The carbon dioxide level increases powerfully. The temperatures rise. On land and in the sea, the heat is unbearable, but the worst is yet to come. The level of oxygen in the atmosphere drops dramatically. The face of the Earth is changing. New cracks appear. The Pangea is torn apart. 50,000 years after the beginning of the eruptions, the Earth shows a sad landscape. The abundant and lush vegetation has become non-existent. What once existed has dried up. The fires continue. The sky is tinged with red. The atmosphere is polluted, rich in carbon dioxide and poor in oxygen. In addition, there are ash storms that swallow up the few remaining survivors in their path. Then mixed with water vapor, these ashes give rise to acid rain. The little vegetation that remains is eradicated. The rains carry the corpses of flora and fauna into the waters. The ocean becomes a giant garbage can. The carbon dioxide dissolves in the water, making it acidic in turn. The plankton, the base of the food chain, is affected this time. The Earth is unrecognizable. Famine strikes without exception. Bacteria proliferate. Pangea is totally transformed. The cracks extend over thousands of miles and miles, and the amount of magma spill reaches 2 million square kilometers, almost 1 million square miles. It is only 500,000 years after the beginning of the catastrophe that the eruptions stop. Pangea was a distant memory, and the Atlantic Ocean was born. In total, more than 75% of the species disappeared. The toll on Earth was tragic, but the ocean suffered even greater losses. The coral reefs have almost all disappeared. The planet is emptied, and yet the world as we know it today was born. Distinct continents are now established on the surface of the Earth. Our future now depends on the few survivors of the catastrophe. The air is unbreathable, and the carbon dioxide level in the atmosphere has never been so high. And yet, a few early animals have managed to survive this cataclysm and adapt to this environment. On land or in the seas, it is the hecatomb, and the calm dominates. Two continental blocks are formed, Laurasia and Gondwana. It is in this miserable environment that the marine and terrestrial fauna and flora will have to develop. The advantage is that many ecological niches are now vacant. The misfortune of some always makes the happiness of others. If when Pangea was still in place, the climate remained dry in its center, it becomes hot and humid, following its fragmentation. The vegetation takes advantage of this new environment, favorable to its blooming. The abundant jungles do not delay to dress the face of the earth, and to revive the papillae of the herbivores. They become numerous and of respectable size. These herbivores become quality prey for carnivorous predators that also reach disproportionate sizes. The reign of the dinosaurs begins. They established themselves on the planet until 66 million years before our era. On land, many archosaurs are still present. They live side by side with large dinosaurs, like the Diplodocus and the Brachiosaurus. The Diplodocus is a giant that measures up to 30 meters or 100 feet long, the equivalent of a basketball court, with a gigantic neck that can exceed 6 meters or 20 feet in length. Its head appears proportionately tiny, housing a brain the size of an orange. Herbivorous by nature, it catches vegetation with its long and fine teeth arranged in a rake on the front part of its jaws. Its tail consists of 80 vertebrae and measures 14 meters, or more than 45 feet. Its 4 columnar limbs support its substantial weight, but it also relies on its tail to lift its body and pick up conifer branches up to 15 meters or 50 feet high. Diplodocus regularly crosses paths with its size rival, the colossal Brachiosaurus, another herbivorous giant. The latter has a similar appearance: large body, long neck, and very small head. It moves slowly through the vast forests of conifers and ginkgos. Although herbivores populate the earth generously, they also become prey for theropod dinosaurs, which also spread all around the globe. Carnivorous monsters of exceptional size, threatening, like the terrible allosaurs, megalosaurs, or ceratosaurs. The Allosaurus literally translates as strange lizard because of its apparent bumps on its skull. It is quite large compared to other theropods, reaching up to 9 meters or 30 feet in length. It is ferocious and feeds on meat from weaker animals. Its robust limbs with powerful claws are totally adapted to hunting. Its tail allows it to balance itself against the substantial weight of its body. But the theropod dinosaur that remains the undisputed superstar of dinosaurs to this day is the Tyrannosaurus, also known as T-Rex, literally the king of the tyrant lizards. This active predator treads the Earth's surface with strides of up to 3.75 meters or 12 feet. From its height of 4 meters to 6 meters, or 16 feet, it uses its olfactory senses to locate its food. Tyrannosaurus is one of the most violent and terrifying creatures that ever existed. Its elongated head alone reaches 1.5 meters in length, or almost 5 feet long. Its teeth measure 30 centimeters or 11 inches from tip to root. Its very short upper limbs are topped by claws and are very useful for grabbing and holding its prey. Other animals have to be careful with this carnivorous monster. The battle rages on Earth. In the midst of huge dinosaurs, smaller species are adapting to survive. Some evolve and get wings. This process is done slowly. They would have been running animals, which, by waving their arms, the beginnings of wings covered with feathers, would have succeeded in accelerating enough to lift themselves off the ground. The species that brings to light the first winged dinosaurs is the Archaeopteryx. This animal is covered with feathers, except on its legs, head, and occiput. It has a long tail, an extension of its spine, and claws on its feet and on the 3 fingers of its forelimbs. It looks more like a reptile than a bird, but Archaeopteryx is an intermediate form between reptiles and birds. The appearance of feathers occurs place initially to ensure a better insulation. Then, the feathers lengthened and ensured, in addition, a locomotor role. But Archaeopteryx is not yet fully adapted to flight. Its bones are dense, which gives it a weight too high to maintain itself in the air. The seas of the time have reefs in places that support diverse species of fish and a wide variety of marine life. Rudists, a group of marine bivalve animals, play an essential role in the development of these reefs. Frequenting warm, shallow waters, they filter seawater to feed on suspended organic particles. The rudists live fixed on the seabed with the help of one of their valves. They can reach up to 50 centimeters or 20 inches in diameter. While some live alone, others form real colonies. Placed against each other, they associate with corals, sponges, and algae to build real reefs. Laurasia and Gondwana are the 2 continental blocks present. Laurasia splits into 2 parts and reveals the future North Atlantic Ocean. 5 million years later, the southern part also opens. The Earth begins to take a familiar appearance. The climate is rather warm because there are no ice caps. The level of the oceans is high, and the temperature of the latter reaches about 10 degrees higher than our current oceans. Marine reptiles still dominate in large majority. Ichthyosaurus gave way to a newcomer, the terrifying Mosasaurus. This marine animal can reach the impressive size of 17 meters or 55 feet in length. It lives in the open ocean, several kilometers or miles from the coast. It moves by undulation, like the current crocodiles, which requires a lot of energy. It feeds on fish, birds, sharks, turtles, but also on other animals of the Mosasaur group. In the air, the small pterosaurs now show quite respectable sizes. The Quetzalcoatlus measures 15 meters or 50 feet in wingspan. On land, the huge dinosaurs still dominate. New species appear, like the Triceratops. Adorned with 3 large horns on its head and a bony ruff, it is intimidating and can protect itself in case of attacks from other dinosaurs. It is not uncommon for it to have to defend itself from the huge T-Rex. Possessing at least 30 rows of teeth, this herbivore can tear up and crush even the most perennial plants. The mammals are there, small and discreet in the shadow of these giants of nature. In the animal kingdom, they have no importance at the moment. Flowering plants called angiosperms appeared as the climate became more humid and the atmosphere became richer in oxygen. They settle in places where conifers have not succeeded in establishing themselves. They are characterized by the presence of ovules inside grains which are contained in a closed cavity. They colonize at first the humid places when they gain the undergrowth of floodplains, the coastal swamps. Barely 30 million years after their appearance, they are already diversified and abundant and rapidly occupy all available ecological niches. The vegetation landscape was profoundly modified, and the ecosystems evolved strongly. Insects, which were present long before flowering plants, specialize in part as consumers of pollen, an energetic commodity, very rich in protein. Moving from flower to flower in search of food, they spread the pollen that sticks to their legs without knowing it. A fruitful alliance between flowers and insects is established. Herbivorous animals develop and diversify, but also granivores, frugivores, and insectivores. A few tens of millions of years later, the terrestrial ecosystem is totally transformed. The forests that remained became covered with colors, fruits, and berries. Flocks of pollinating insects parade in the middle of this vegetation. Huge herbivorous dinosaurs feed on all this food during the day, and small lizards, birds, and mammals are busy eating the leftovers at night. It is now more than 160 million years since the immense and majestic dinosaurs dominated the Earth. A world that has been slowly built up and is about to be annihilated, marking the fifth and last great crisis of life. No animal can see the danger coming. It is about to fall from the sky, slyly, at the speed of several kilometers per second. Billions of tons of asteroids are ejected. One of them is heading towards the Earth, like a real bomb. The shock is terrible. The meteorite hits so hard that a crater of 30 kilometers or 20 miles deep is drawn. An energy of a monumental intensity is released, causing the transformation of the rock of the Earth's crust into liquid element. Within a radius of 60 kilometers or 40 miles around the impact, the water turns into water vapor, and animals are immediately killed. Within seconds of impact, the shockwave reaches the ocean before dissipating. Everything in its path is literally vaporized. The consequences will soon be felt. The impact of the meteorite causes an earthquake of unparalleled intensity. The animals that did not fall into the crevices try to find shelter, but the catastrophe does not stop there. A wall of water, as big as a mountain range, rises and falls on the coast. The tsunami spares no one. On land and in the sea, everything is swept away, washed away and thrown on the shore. As the Earth tries to catch its breath, the rocks that were propelled during the impact fall back. A shower of whole pieces of the Earth's crust falls on the Earth for several hours. The temperature of the atmosphere rises to more than 500 degrees Celsius and 930 degrees Fahrenheit in places. All creatures are vulnerable to the cataclysm. The planet is unrecognizable. Billions of animals will die. In the seas, 76% of species and 15% of families will become extinct forever. On the continents, 6% of families will disappear. Although the most famous crisis, the Cretaceous extinction, is nevertheless the most modest in terms of extinction rate. Biodiversity is still heavily impacted. Ammonites, large marine and terrestrial reptiles, disappeared, and the field was left open for small mammals to multiply and grow. Several months after the impact, the Earth undergoes a return to cold. The heat released by the meteorite has generated large quantities of carbon dioxide, which absorbs the heat. The Earth is about to live a long winter before finding a more stable climate. India, which was part of Gondwanaland, was slowly separated from the continent a few million years ago. It was wisely heading south, but was deflected and oriented north. As the plate crossed the Tethys Ocean, it passed over a zone of hotspot volcanism and saw its course accelerate. Its sudden displacement leads it to Asia, which it violently collides. India sinks under Asia at a speed of 2 centimeters or 0.8 inches per year. As a result, its crust is lifting and overlapping like scales on top of each other. India's crust thickened, and a mountain range was formed several million years later, the Himalayas. Northern India is compressed and loses 1,000 kilometers or 620 miles of extension. The fragments ejected from Asia will give the Southeast Asian bloc the archipelago of Indonesia and the Japanese archipelago. The face of our current planet continues to be assembled in the manner of a puzzle. The Earth is perpetually subject to earthquakes and volcanism. A strong volcanic episode that started around 60 million years ago releases a large amount of CO2. The lower atmosphere and ocean waters warm up initially. In the long term, the increase in greenhouse gases causes a rapid and generalized warming over the entire surface of the Earth. Ocean surface waters rise by 5 degrees Celsius, or increase by 9 degrees Fahrenheit. Greenland, Alaska, and Siberia are being covered by subtropical forests. This warm and humid environment is conducive to the development of life and coincides with an evolutionary radiation of mammals. The large extinct reptiles have left free niches, and mammals intend to take advantage of it. Some animals will develop to the point of mastering swimming or flying, like whales, dolphins, or bats. Primates, horses, and primitive deer start their different lineages. Birds multiply, and some species reach impressive dimensions with more than 2 meters in height. Insects and flowering plants continue to evolve with each other. In the Frankfurt area of Germany, a violent volcanic eruption leaves a large, deep crater open. Quickly occupied by the waters of a lake, this crater shelters an abundance of fauna and flora, allowing life on the surface. Amidst 1,000 diverse species of plants and animals, a small mammal stands out as the oldest common ancestor between the lineage that led to humans, monkeys, and lemurs. Darwinius massillae, better known as Ida, is morphologically close to present-day lemurs. It measures 1 meter, or 3.2 feet in length, and weighs between 650 and 900 grams, i.e., between 1.4 and 2 pounds. It is herbivorous and feeds on seeds, leaves, and fruits. It has a particularity. Its thumb, opposite to the other fingers, allows it to grasp, which brings it closer to primates. It also has no claws on its fingers, normally used by lemurs, and has a bone structure on its feet, the talus, which is similar to that of monkeys. It is situated before the separation of the two lineages, leading on one side to the monkeys and on the other to the lemurs. The life that remains in this crater lake is suddenly wiped out, probably by upwelling of carbon dioxide from the bottom of the lake. The animals are subjected to a rapid death. After the warm period, ocean circulation and plate tectonics lead to a cooling of the Earth. A current prefiguring the Gulf Stream weakens and sea ice gradually settles around and over Antarctica. It accumulates to the point that mountain glaciers are formed. A current that thermally isolates Antarctica is established, the Antarctic Circumpolar Current. It is the most powerful current on Earth. This current connects the oceans in the southern hemisphere and plays an important role in the circulation of waters of different salinity and temperature. It is cold, contains dissolved gases, and is one of the main reservoirs of CO2. The complete opening of Antarctica permanently cuts off ape populations from the New World, the Americas, and the Old World with Africa, Asia, and Europe. Some primates that remained on African lands managed to reach the American continent. Did they cross the Atlantic Ocean on floating natural rafts, or did they travel through chains of emerged volcanoes? The method is still unclear, but they settled in the forests of the New World. They will later be at the origin of tamarins, marmosets, or other howler monkeys characterized by their tails that wrap around the branches. The platyrrhines owe their name to the shape of their nose, which is flattened and equipped with a thick septum and large nostrils directed towards the outside. The catarrhins, or Old World monkeys, arrived from Asia on the African continent. They owe their name to their nostrils positioned on the sides. Africa appeared to them as an ideal place to live, and they gave birth to two different groups. The Cercopithecids, equipped with a tail that serves as a balance, and the hominoids without a tail. These last ones know a consequent development almost entirely concentrated in East Africa. "20 million years ago, the first proconsuls appeared. These quadrupeds use their forelimbs of identical length to climb trees. They will diversify and give birth to species of all sizes. It is at this time that the group of hominids appears, which gathers the current chimpanzees, gorillas, orangutans, and the man. 18 million years ago, the African continent and Asia collided. This collision will have an impact on the evolution of human history because 2 million years later, the seas are lower and the apes can then move to Eurasia. Western and Central Europe were then covered with luxuriant forests, an environment that favored the evolution of Old World monkeys that gave birth to the gibbon. The mode of movement by hanging from trees is widespread. Their arms are longer than their legs, and their hands are larger, with curved phalanges. As these monkeys straighten up, their pelvis and spine also become more rigid. Toumai, ancestor of the man. The hominin lineage separated from the great apes 7 million years ago. Toumai, which means hope of life, is the oldest known hominin representative. The region of Chad, where Toumai was found, enjoyed a generous climate at the time. In the heart of savannas teeming with life and forests bordered by lakes, Toumai, a small being of about 1.20 meters or 4 feet for about 30 kilos or 60 pounds evolved. Other species live alongside him, such as crocodiles, elephants, small rodents, fish, and wild pigs. Facing them, predators and scavengers include species close to hyenas and felines. Toumai and his fellow creatures did not have an easy life. Despite their probable bipedalism, they are not adapted to running, although they can also run by leaning on their phalanges. Unlike chimpanzees, they do not have large canines to defend themselves, and therefore rely on their sense of smell, hearing, and sight to protect themselves. Their group spirit is also an asset. They are certainly vegetarian, with a diet based on fruits. Toumai has primitive features and a cranial capacity equivalent to that of the chimpanzee, which does not prevent it from possessing considerable intelligence and a certain social structure. Toumai is a unique mixture of morphological characters, different from what is observed in chimpanzees and the ancestral species of man. 6 million years ago, Auroran roamed the lands of present-day Kenya. With both simian and human characteristics, the features of its humerus and femur bring it closer to modern man than to Australopithecus. It is clearly bipedal and arboreal, as shown by its curved phalanges. It feeds on fruits and is the prey of fearsome predators, such as large carnivores. It lives in an environment of dry evergreen forest, interspersed with wetlands. A little taller and heavier than its ancestor Toumai, some measure 1.4 meters or 4.5 feet, weighing nearly 50 kilograms or 110 pounds. A little after Toumai and Auroran, the Ardipithecines lived just before the arrival of the Australopithecines. At that time, fire was not mastered, and living conditions were harsh. Tools had not yet been perfected. Bipedalism is again invoked for this genus. These 3 species that lived between 7 and 4 million years ago are at the base of our phylogenetic tree. They are a bit of an intermediary between the primate ancestors and the Australopithecines. The Australopithecus genus is found mostly in central, eastern, and southern Africa, in savanna areas near rivers and lakes. It is not before 2.5 million years that they migrated to Asia, then even later to Europe. Allow them to eat an omnivorous diet. As early as 2.5 million years ago, the most recent Australopithecus in the forested and wooded areas they inhabit. At night, they are able to build themselves a shelter of leaves. They eat fruits, leaves, insects, and sometimes meat. Australopithecines, whose game among herbivores, elephants, giraffes, wild pigs, and small rodents. Their activities are organized around hunting and gathering. However, they are limited in hunting due to their poor equipment. The Australopithecine group was made famous by the discovery of Lucy in 1974, which was then the oldest hominin fossil discovered. Near the Awash River in Hadar, Ethiopia, several hundred bone fragments of lower limbs and jaws belonging to a single individual were found at an excavation site. It is the first time that such a large proportion of bones from the same individual is found. 52 of the 206 bones that make up the skeleton of an Australopithecine. The study of her pelvis confirmed that she was indeed a woman. Lucy has many simian characteristics. Her flared rib cage, a large stomach, and consequently, a vegetarian diet. Lucy is about 1.10 meters or 3.6 feet tall and weighs about 25 kilograms or 55 pounds. Its joints, shoulders, long arms, and short legs testify to an arboreal life in parallel to its bipedalism. This discovery totally changes the conceptions of the origins of the human lineage, but it will still take some time before we arrive at modern man. Before 2.5 million years ago, the two Americas were home to very different faunas. The Central American Sea separates the two continents of North and South America. The waters of the Pacific and Atlantic Oceans mix. At the bottom of the oceans, a pressure is exerted, causing the Pacific plate to rush under the Caribbean plate. The pressure and heat that occur during the collision form volcanoes under the seas, visible in the form of small islands that emerge. The movements of the two plates cause the seabed to rise above sea level. Over time, the open spaces between the newly formed islands are filled in with sediment until a complete closed isthmus is formed between South America and North America. This is the Isthmus of Panama. The creation of a bridge between the two previously separated lands promotes a migration of plants and animals called the Great Inter-American Exchange. Organisms from South America reach the north, such as porcupines, opossums, anteaters, armadillos, and pangolins. Conversely, horses, deer, elephants, and raccoons from the north settled in South America. For 1 million years, this transfer remained equal in exchange. Then, the mammals of the north continued to live and settle in the south, but those of the south became extinct or few in number in the north. 2.4 million years ago, new hominids appear, whose morphology is sufficiently different from that of Australopithecines living at the same period. They form a new genus, the Homo genus, to which our species Homo sapiens belongs. But it will be necessary to wait a little more before the latter appears. 3 main criteria distinguish the Homo genus: an exclusive and permanent bipedalism, a cranial capacity that became more important, accompanied by a flattened face, and the implementation of cultural activities such as artistic creations or the use of fire. Homo habilis is the first representative of the Homo genus to appear. It measures between 1.30 and 1.50 meters, that is, between 4.2 and 5 feet, and weighs between 30 and 40 kilograms, that is, between 66 and 88 pounds. It is a little larger than the Australopithecines. Physically, its teeth are smaller. It has elongated arms, sturdy legs, and curved phalanges. His hand is not freed from locomotion, and he still retains arboreal abilities. With Homo habilis, the production of tools intensified considerably, hence his name, skilled man. His diet became richer in meat, and he became omnivorous. As a perfect scavenger, he uses his tools to cut the meat and break the bones of the bodies of large mammals to extract the marrow. Appearing in the African cradle 1.9 million years ago, Homo ergaster took a decisive step in the history of the human lineage. He left the branches of trees and evolved essentially on the ground. This new mode of locomotion changes considerably his way of life. He appropriated fire and carved complex tools such as bifaces, Homo ergaster is an excellent walker and can even run over long distances. From the top of its 1.55 to 1.70 meters, that is to say, between 5 and 5.5 feet, and its 60 kilograms, or 130 pounds on average, it resembles more the modern man. It makes, for the first time, exits out of Africa with the aim of finding meat, which is necessary to him in order to nourish its brain and body in growth. Homo erectus is the first hominin with a brain volume exceeding 1,000 cubic centimeters, approaching that of humans, who average 1,350 cubic centimeters. This implies a strong need for meat. Its teeth, smaller than those of other hominin species, are also adapted to this new diet. It measures between 1.50 and 1.65 meters, or between 5 and 5.4 feet, and weighs, on average, 50 kilograms or 110 pounds. Although he was not the first to venture out of Africa, he was the first to travel very long distances, thanks to his fully mastered bipedalism. He set up camp as far as Asia and Europe. Homo erectus mastered fire and made tools carved in stone, such as symmetrical bifaces, axes, and scrapers. He created a real society gathered around fire. The hunter-gatherers form a real group within which each one takes care of the others. It is in this social and family environment that Homo erectus takes care of his descendants by providing them with the energy necessary for the development of their brain. Of a more massive and stocky aspect with rather short arms and legs, the Neanderthal man resembles morphologically the current man. He measures between 1.50 and 1.70 meters, or between 5 and 5.5 feet, and weighs between 50 and 70 kilograms, or between 110 and 150 pounds. Its cerebral volume can reach up to 1,750 cubic centimeters, that is to say, more than that of the Homo sapiens. It is gifted with emotions, skilled in handling tools, and capable of dialogue and creating a culture. He practiced funeral rites, which shows that he apprehended death as a stage in his existence. After its appearance in Europe, it occupied all of Eurasia, from the British Isles to the Russian plains, via the Middle East. It is capable of adapting to very different environments and significant changes in climate. It coexisted for some 10,000 years with Homo sapiens, but then disappeared. The human lineage differentiated from other bipedal hominids 2.4 million years ago. Homo sapiens made a late entry into Earth's history, but his footprint and success are remarkable. 200,000 years ago, the species to which all humanity belongs, the only survivor of the other Homo, settled on the planet. He measures between 1.50 and 1.75 meters, or 5 and 5.7 feet, and weighs between 50 and 70 kilograms, or 110 and 150 pounds. His skull is rounded, his chin bony, and his skeleton light. In spite of difficult beginnings, it manages to colonize the Earth. He organizes himself, assembles himself, and settles in fixed places. He settles down. Hunting and gathering, which until then had been a matter of survival, gave way to agriculture and animal husbandry, which ensured stable food resources. Homo sapiens learns to master the natural environment which was previously rather hostile to him. This capacity of adaptation allows him to spread over all the regions, even the most difficult, of the planet. He shapes the landscapes and takes in abundance wood and other materials for his comfort and his needs. His success is such that his population will not stop increasing. Just like Neanderthal man, Homo sapiens buried his dead. As populations grouped together and interacted, culture spread, notably with the development of various forms of art through paintings and statues. Science and technology spread, leading to a better knowledge of nature and the design of quality tools. Homo sapiens spreads and replaces the other human species, which become extinct at its contact, without knowing exactly the reason. The last Neanderthals are observed in the Iberian Peninsula 28,000 years ago. Homo sapiens remains the only species of the genus Homo on Earth. From now on, cultural evolution takes precedence over biological evolution. Symbolic thought and art literally explode. It develops ceramics, invents new weapons such as bows and arrows, and assegai thrusters. All hominins share the common character of bipedalism. This posture is a major asset that allowed the liberation of the hands, making them available for the elaboration of tools. But the sitting position is also largely contributed to perform tasks using the hands. When they are freed, they become creative. The human hand has adapted. The thumb has developed in opposition to the other fingers. The wrist joints generate a firm grip. The fingers can fold around an object to adapt to its shape. The evolution of the nerve centers and the tactile sense influences the development of the hand and gives it useful skills and sensations. In spite of the physiological evolution of adaptation to its environment, the newborn of modern man keeps certain archaic reflexes, some of which will persist throughout life, such as the breathing reflex, the yawn, the sneeze, the fluttering of the eyelashes, the cough. The hypnic jerk is a reflex that translates as a jerk during sleep to catch up with the branches. Over thousands of years, modern man domesticates plants and animals. He settled in the Middle East in the Fertile Crescent to develop agriculture and livestock. He developed an economy of production, no longer of predation, a sedentary and urban habitat, the use of ceramics, metallurgy, and the wheel. And finally, he invented writing, which marked his entry into history more than 5,000 years ago. His sedentary life constitutes a radical turning point in the history of humanity and a revolution in the environment. Natural environments were modified, first to a limited degree in villages, then on the scale of entire regions. The herds multiply, and their immoderate appetite for vegetation is the reason for the natural landscapes. Agriculture and livestock are deployed with increasing intensity. Man nibbles the forest to obtain timber and firewood. He develops environments more suitable for his livestock and his crops. The natural space is no longer wild, but artificial. During its 5,000 years of history, Homo sapiens multiplies its numbers by a factor of 1,000. A growth of the population, coupled with an unlimited consumption. The Earth, which ended up being shaped geologically in the image of the one we know today, gave him free rein to develop. It then crisscrossed the entire planetary surface. But it is during the last 2 centuries that it increases its knowledge in an exceptional way. Its technological part grows and becomes more complex. It consumes energy and raw materials in a bulimic way. a management of the resources not sustainable in the long run. The planetary pollution generated is so consequent that it could lead to the next mass extinction, of which it would itself be a victim. Animal and plant species are confronted in nature with the destruction of their ecosystems by the activities of modern man. Global warming is endangering the natural balance between air, water, animals, and plants. It is too late to turn back the clock, but far from too late to act and prevent it from getting worse. Human intelligence and technology are opening the doors to a possible future. Homo sapiens is now leading his evolution. He is able to change his way of life and to exploit the planet's resources in a rational and measured way. Because the Earth is far from having said its last word, the history of life on its surface is still going to know many evolutions.